a bit too convenient. Life was like that. I didn't choose it. Yeah?
Okay, well, thank you very much for putting our paper on the program. So we're going to be talking about estimating the aggregate implications of incomplete markets using an incomplete model. So this is joint work with Marcus, who is no longer with us, with Yuri, who is online, and Sean, who's here in the audience. So what we're really after in this paper is trying to kind of answer the question of how important are incomplete markets for aggregate dynamics, business cycle fluctuations. And also we want to know how important they are for counterfactuals, how they alter aggregate responses to monetary and fiscal policy. So what's the way that we would usually go about answering these two questions? Kind of the one approach is you just write down a fully specified quantitative Hank model, you solve the economy. The cost of that is that you have to specify the full household block. The benefit is that then you can do kind of whatever counterfactual can be accommodated in your model. There's another approach, which is kind of less structural, which is thinking about kind of projections of the impact of household redistribution on different kind of aspects of the economy. So Luigi is not here, but kind of his paper in the QJE was thinking about how we can use microdata directly to kind of develop a stochastic discount factor or pricing kernel to give a representative agent representation, which can be used for like an ex post accounting of realized history. Or we can think about kind of sufficient statistics to capture aggregate demand. These approaches require less structure, but for counterfactuals, they're really only valid in the policy environment in which they're measured. So where do we come in? So we want to think about trying to identify this underlying redistribution itself, kind of from the data, and use that to be able to answer both questions. How are we going to do that? Well, kind of the central object that we're going to build this paper around is really thinking about a household level redistribution mapping. So instead of kind of writing down a fully specified model where we're going to say kind of how everything happens at the household level, we can want to just measure it kind of directly from household budget constraints. So then the kind of thought experiment is, let's think about we have kind of an equilibrium path of a complete markets model. We call like this benchmark path PR, which is going to be a path of prices and quantities. This delta, which is going to be the object that shows up kind of throughout this paper, is going to be this kind of mapping, this compensating transfer sequence that's going to make households, kind of household by household, reproduce kind of exactly their counterpart in this candidate rank allocation. So thinking about a representative agent model, you give households some transfers, they're going to move up and down the way that all of the representative households would move in rank. And so this mapping is going to basically come from a candidate path, so think about a rank model, and budget accounting, not from solving the model itself. That's the basic idea. And we're going to show that we can kind of take this very far. So why is this useful? So, like I said, once we have these deltas, one, we can use them to kind of measure the difference. That gives us the measure of how much redistribution is doing, kind of combined with incomplete markets directly from microdata. Now, I said that kind of what we need is kind of a candidate path, this like representative agent path, combined with budget sets to get things. Of course, the data, we think the DGP is probably something from Hank, so we need to identify this kind of latent representative agent benchmark to get the redistribution, and we're going to show that we can do that, and that we can essentially estimate a Hank model kind of without specifying the household block. That's going to be kind of the deliverable, and that estimated model is going to be useful for counterfactual analysis. So I'm going to show you the kind of, we change monetary and fiscal policies, this kind of latent rank Hank model is going to capture what a true Hank model would do. So kind of a rank component plus a redistribution component is going to give us Hank. How are we going to do that? I mean, it's, yeah.
Just to break the ice.
Yes, yeah. Yeah, feel free. I mean, I can talk here, but it's more fun if.
Is it unique, the redistribution? Or it depends, yeah.
Yeah, so this is going to be the unique map. Yes, unique map. A unique map, yeah. So how are we going to do this? So this is kind of the sequence of events, or things of steps we're going to do. This is the thought experiment. We're going to start off with some rank kind of impulse response. Let's say to a monetary policy shock. That's going to give us prices and quantities of path. We're going to combine that with information on household budget constraints. That's going to tell us how to construct these compensating transfers, this redistribution map. Now that's going to kind of tell us some quantities of how much redistribution there is. then kind of the next step, we're going to aggregate that with kind of information on IMPCs, so intertemporal marginal prices to consume across households. Then we can kind of aggregate from the redistribution to thinking about how much does that move aggregate consumption relative to rank. Of course, that's going to be kind of a partial equilibrium move, and then we kind of have to think about how we're going to close the aggregate block in order to kind of recover a Hank GE. And I'm going to show you kind of that we can do all these steps, and all you need are things essentially that you can measure from the data plus kind of a candidate rank model. So, we measure the redistribution from budget sets. You need information on NPCs, and then we just kind of need to feed it through GE. That's how we're going to go from rank plus budget sets to Hank IRF without ever specifying, what is the incomplete markets kind of part of the model.
Sorry.
Yeah.
Does this mean that this redistribution bit is orthogonal to the general equilibrium stuff that the rank gives you? If you can go through the sequence and be back where you would be with Hank, is that correct?
Yeah, so I guess our thought experiment is basically the only difference between rank and Hank is rank consumption is from an Euler equation. Hank, it's from aggregating a bunch of Euler equations. Everything else we think is going to be common. So once you move consumption in a different way, we kind of assume that the feedback from the rest of the system is the same.
But my question is that an assumption or that again, like this redistribution that you're doing, you can do it without knowing anything about the general equilibrium stuff. So
Yeah, so that is without knowing anything about the general equilibrium stuff. I'll show you kind of the exact assumptions that we need, but it is without, I'm going to specify just paths without ever specifying the production side or anything else, kind of just focusing on the household block. Yeah?
I understand how this might work for a monetary policy, that was your example, but say you take a simple fiscal transfer example, so then the rank model would have no effect. Is that where you would start from? Or?
Yes, so the rank model would have no effect, but we would still feed in, the government budget constraint has to hold. So then the first round compensating transfer is going to be essentially undoing the transfer experiment, which is then basically your PE deficit finance transfer, and then you build into the GE. Right, so
I still don't see how you get to rank, because I understand, you're talking about pure redistribution, but in this case it wouldn't be, right? There would be like sort of an aggregate effect in the Hank model.
yes, and so that's what kind of the last part we're going to have. So it's like, essentially, think about, I'm going to show you, we do it for deficit finance transfer, yeah. But yeah, that basically gives us the PE, and then this is going to close the block. Okay. So in some sense, like, IKC is kind of part of this step. Once you have the IMPCs, that's kind of one of what we're going to get. Okay, so what I'm going to do for today, or I guess with the roadmap for the paper, is essentially I'm going to put together this model light estimation procedure that's going to take into account this kind of redistribution that's measured in the data. Again, we're going to use this to estimate the kind of the latent rank model that we need that we kind of think would underlie what we see from a DGP generated from Hank. And then, we're going to use that to recover this latent rank. Then we're going to do kind of Monte Carlo experiments on model-generated data from leading Hank models and from people in this room. And then we're going to show is that if we kind of generate impulse responses from these Hank models, we can estimate a rank model directly, which is going to be misspecified. Then we kind of show, as you might expect, that it's going to give you biased parameters and the counterfactuals are going to fail relative to the truth. And then we're going to estimate kind of our latent rank Hank model. We're going to show you that we can recover parameters kind of with negligible bias, and that we predict the effects of counterfactual policies. So if you change the Taylor rule, if you do a deficit finance transfer, the latent Hank is going to capture that kind of very well. So that's what we're going to do. So this is like pure methodology paper, so I'm not going to give you an answer to the first two questions. I'm going to give you a methodology of how you can go out and answer that question yourself. Okay. So what are the basic ideas? So this kind of gets to what do we need? Like what are the kind of the set of models where this will kind of our procedure is going to hold? So I'm going to start off. We need to kind of specify what is the household budget set, or what are the kind of things that we could see in the data. Here again today we're working off the model. So we're thinking about just a standard household budget set. Consumption and savings are financed out of asset income, kind of after-tax earnings, where we have this retention function. So the retention function has to be kind of homogeneous of degree 1 minus tau p. So this kind of an HSV function is fine. If tau p is 0, you think about just linear taxes. And then there's some transfers that households receive, where this lambda IT says that households could be receiving kind of different levels of transfers, and there could be heterogeneous returns on household savings. So the idiosyncratic state, this S is going to be kind of the stochastic labor component. That's going to be exogenous. And again, we're going to take these kind of how many transfers you're receiving, and the returns are going to be exogenous. This is kind of the budget set, the thing that we want to try to measure. What do we need kind of for assumptions on the model for when this is going to hold? So we want to get everyone in the Hank economy to move up and down, kind of to scale proportionally with like the representative agent would. What does that mean? That basically means we need first order conditions to be homogeneous of degree 0. Then if I kind of scale, if I scale your budget sets, if I scale everything, everything's going to scale, and it's all going to work. How can we get that? Well, we need separable preferences between consumption and leisure. We need CRRA so that we can get it to be homogeneous to degree 0 in the first order condition. So we need to have a kind of the same coefficient of relative risk aversion across people. On the labor side, we kind of can show that there are two cases where it works. What we're going to think about today is kind of rationed hours, so kind of unions, sticky wages, households are off their labor supply curve. You know, you could pick whatever arbitrary labor utility function that you want. And you can also allow for unequal incidence as long as it's kind of depending on exogenous types. We can have flexible wages. If we have flexible wages, then this utility has to be isoelastic, and there has to be a common Frisch elasticity. Again, that just gives you that the FOCs are going to be homogeneous. So then what could be heterogeneous? You know, households could have different discount factors, labor disutility, the transfer incidence, the heterogeneous returns. You know, what do we need? We need common risk aversion, common Frisch elasticity. And if you have nonlinear taxation, you kind of need a common progressivity parameter. Yeah?
And something on the borrowing constraint as well.
Yeah, so the borrowing constraint, so we need basically the borrowing constraint to scale. So if it's 0, it's 0 or it needs to scale.
Same question.
Okay, yeah, that's right. There was a, yeah. We need this, we're going to need this asset set to scale. Yes. So for the rest of the talk, I'm just going to focus on like what I call the leading case, which is kind of, if you think about like, you know, Ludwig and Adrian's kind of canonical Hank model, like basically looks like that. There's a linear tax, there's union hours with equal incidence, there's no borrowing, there's no heterogeneous returns, kind of a simple one asset Hank model. So the canonical Hank model is going to be our leading case. Yeah.
You don't need the government budget constraint to scale,
We need the government budget constraint to hold.
but not to scale. So
No.
you can have public spending.
Yes, you can have public spending. Yes, yeah, exactly. So here, all these deltas are going to be a pure redistribution, so they have 0 impact on the government budget constraint. It's just reshuffling resources across
You
people.
only need the first order condition to scale and not to release the rest.
Exactly, exactly. Okay, so how do we construct these transfers? Like I said, the thought experiments, we kind of start off with this kind of benchmark candidate rank response. So let's think about an economy that has some steady state aggregates, consumption, assets, hours, output, wages. And let's think about some deviation from this steady state. That's going to give us kind of these proportional responses for consumption, assets, hours, output, wages, transfers, and taxes. And that's going to be kind of the proportional movement of the aggregates in response to kind of whatever shock. Think of a monetary policy shock. Now, if you think about how all of these components are moving, if we think about a household budget set, kind of generically, there's going to be heterogeneous movements across households in terms of their resources. So, you know, if hours move up a lot, people who mostly finance consumption out of labor income will gain relative to people who mainly finance out of assets. So what we're going to do is essentially compute these transfers to make it such that all resources are going to scale in proportion to the aggregate. So we're going to make something kind of like equal incidence of total income for these people, so that everyone's going to move up and down with the aggregate. So the way to think of it is that it's just a homogeneous shift in proportion to the aggregates. So those deltas say, like, how many resources do I need to give you to get you to all of your resources to move in the same percentage as kind of what the representative agent would. So these are not arrow securities. We're not completing markets. It's like there's an Iagari steady state where everyone's moving around. If aggregate consumption goes up by 1%, aggregate consumption in that whole moving around moves up 1%. That's the idea. It's just a shift. I mean, Ivan kind of made this point very cleanly in his incomplete markets and aggregate demand paper. I mean, it was kind of related, very related to that. In his simple model, he had consumption equal to output. Individual income was proportional to output. This basically gives that there's proportional income changes with output. So when output moves, my income in proportion to aggregate income kind of moves the same way that Adrian's would, and so we have equal incidence, and so you get that rank and Hank coincide in response to a monetary policy shock. Obviously, kind of typically in the data we think that this doesn't hold. You can imagine because there are transfers or there's assets, other things that would break this unequal incidence. But kind of in this simple model, what you can think about what our deltas are doing is we're basically just constructing the deltas to make kind of this equal incidence of income hold again. So we just pick the deltas for each person that are going to cause perfect scaling, but it's going to preserve the heterogeneity across people. So then, what are we going to do kind of with these transfers? Think about putting the transfers into the household budget set kind of in response to the shock that we're considering. So the dynamic programming problem is kind of the steady state dynamic programming problem. But now we're going to feed in kind of these transfers. And what's important is that the transfers don't depend on any choices. They're allowed to depend on your wealth and your exogenous states, but if you choose to save more or less or consume more or less in the future, that doesn't have any impact on the deltas. They kind of only depend on your endogenous state variable today and the exogenous state variables going forward. So it's a kind of a payment to the household that's non-manipulable. The idea is that we want to construct these deltas such that it's feasible for everyone to scale their consumption and their savings kind of in exact proportion to the aggregate. And if they were on their labor supply curve, also to scale their hours. So how do we do that? I mean, it's basically what I showed you on the voting slide, but now we've got all kinds of other components of the budget set that we have to undo. So, essentially, if your income doesn't move kind of exactly in proportion with the aggregate, we kind of want to undo that income change. We want to do the same, kind of undo the changes that you get in asset income from changes in the real rate. We have to undo kind of changes in income that are due to the fact that you accumulate a different path of assets. So kind of given a real rate, the fact that your asset accumulation is going to be different. And then finally, we kind of need to give you resources to compensate for the difference in consumption. Yeah?
So here you do this for a given guess for the path of aggregates.
Mm-hmm.
You get this fixed point, because like if you do the redistribution, then the aggregate changes.
Exactly. So
that was the later part.
That's a later part. That's going to come for the.
So here you just take a guess.
Here we just here.
But if it's not the right aggregate, it won't average to zero.
That's correct. So yeah, this will only be true if that aggregate. So if that aggregate is actually a rank, is a fully specified kind of rank equilibrium. So here, this is step one. I'm going to make the Hank model look like rank, which is not the same as what would be the Hank GE. So we're doing like.
Okay. So
We're doing
now you just take the aggregate path that you're trying to target as a given.
Yes.
And you
Yeah.
can construct this, and if it wasn't the aggregate, it would not average to
Zero.
zero.
Yeah. Okay. So the idea is that now, what's our desired equilibrium? Our desired equilibrium is that these deviations in wages, hours, consumption is going to be kind of exactly what we get these gammas from rank. So if you put that all together, you're going to get these deltas, kind of, if you get them from the rank path, that just kind of separates cleanly into gamma components, which are from the rank impulse response, and then steady state budget objects. So you don't need to know kind of how people in Hank are going to change in response to a shock. These are just kind of purely steady state budget objects combined with impulse response objects. So there's kind of a separation from what comes from rank and what would come from budget sets. So, again, if these gammas kind of come from rank, this is going to be redistributive, so the deltas are going to integrate to zero, so it's a pure redistribution across households. If the deltas are all identically zero, then we're going to get kind of that rank and Hank are the same. Or also if NPCs were all the same, then you would still get that result. Kind of you need a covariance between the deltas and NPCs to get an impact of incomplete markets. But the idea here is, delta relies on information which, in principle in the data is going to be easily available. For today we're going to do stuff all on simulations, kind of from the model. So we're just going to take what you would observe from a model cross-sectional distribution, and then the aggregate gammas would come from these rank IRFs. So it's something that we can write down and solve a rank model. But we don't really require any information that's specific to the Hank model in order to do this so far, beyond the assumptions that we need kind of on what we have for preferences and the asset space. So this is kind of the main theorem that, these gammas, let's kind of define them. We're going to think about a representative agent model that's proportionally aggregable, which means that everyone, in that representation model is going to scale in the same way. So if the gammas are part of a complete markets model that's proportionally aggregable, then if we have that this complete markets economy is matched to the same kind of steady state as the heterogeneous agent model, has the same aggregate block, same tax schedule, and same kind of elasticity parameters, then, kind of under that household environment that we defined, this incomplete markets economy with transfers is going to have the same aggregates as this complete markets benchmark, and all individuals are going to scale proportionally just like the representative agent. And, we have that the deltas are going to integrate to 0. So kind of given a rank path from a rank model that is proportionally aggregable, combine that with deltas from budget sets, give that to households, then kind of given rank prices, the households are going to look exactly like representative agent households. Yep?
So, sorry to come back to this, but you're calling it the rank model, but I wonder if that's the right benchmark, as opposed to like...
It's not. So, yeah.
Incomplete market, so here's another one. Incomplete market with respect to idiosyncratic shocks, but complete markets with respect to aggregates. So which you could get from like a portfolio choices. And so there, you could solve that model, and in that model, by construction, kind of the portfolios undo the redistribution, so and that would be like that would be a natural benchmark.
Yeah, so I think here what we want to think about is like the real rank benchmark is one we don't observe. So it's going to be latent that we have to estimate. Because we think of like the data is generated from Hank. And so we're going to use kind of this procedure to construct a Hank impulse response, but it's going to require knowing what this latent rank is to use this procedure. And that we don't know, and I'm going to show you kind of how we can get it. Right now, let's imagine you knew some true rank, and you wanted to make kind of Hank get there. So it's.
But I don't know if it's rank. That's what I mean. It's like it seems like it's more complete market. You have a notion of complete markets with these heterogeneous agents and so on.
So I would say that this complete markets economy is not the completion of markets in the heterogeneous agent economy. It's not. So it's a complete markets economy that has the same steady state in terms of quantities and prices as the heterogeneous agent model. So like the the discount factor has to be different.
Okay.
So think about this as a complete markets model that matches the heterogeneous agent one in terms of aggregates and prices, but it's not the completion of the heterogeneous agent model. It's a latent rank device, I guess, that we're going to use. The idea of the proof is actually quite easy. I mean, I have steps here, but basically, once we have everything, that's homogeneous, basically every first order condition we can scale by, some household invariant factor times the steady state first order condition. So that gets all the first order conditions to hold. The deltas make sure all the budget constraints hold. All the rest of the blocks between rank and Hank are the same, and so we're kind of done. It's basically, that's kind of the beauty of the separable preferences with CRA is that we can just, you scale everything, it's homogeneous to degree 0, you pull it out, and everything cancels. Okay. So what does the theorem give us? This says that kind of if you have some benchmark IRF, which kind of, like the discussion with Adrian has revealed, is an object that it's not clear kind of what it is or where we can get it from. But imagine you had this IRF, and you had budget constraints, that gives you kind of the measured redistribution. Then, what you can think about is what's kind of the aggregate impact on consumption kind of from this redistribution. Kind of in partial equilibrium, if you have then information on IMPCs, you basically just aggregate the IMPCs with this redistribution, and that kind of tells you kind of how far the consumption from Hank is from rank. Now, this is not saying that this is going to be the GE Hank object. We still need, we need to have one more step. But this is kind of what the theorem gives us so far. Essentially, at rank prices, a correction of aggregate consumption from rank to Hank. Just to give you a scope, like we kind of talked about this, you can, the theorem is exact. We have linear kind of HSV taxation. The borrowing limit either has to be 0 or that it can be rescaled. We worked out some extensions. We can accommodate 2 asset models, kind of if the adjustment cost function is homogeneous to degree 1, so that the FOC is, again, homogeneous to degree 0. So like in Kaplan-Violante, it works. Kaplan-Violante with the fixed cost doesn't work. We can also do Calvo adjustment costs if there's a constant proportional wedge between the liquid and illiquid asset return, which is exactly from intertemporal Keynesian cross. So Kaplan-Violante we can do, and IKC we can do. We can also work out something with Mankiw-Ries, but there we have to move beyond the proportional because you have to have kind of 2 classes. You have to have the awake people and the asleep people. But that we can do. So I would say that most of the frontier Hank models could be subsumed in this theory. Yeah?
How does your CRM select the credit constraint households? Because if you scale Euler equations, everyone is having a Euler equation and no one is credit constrained.
So, I mean, in principle, we don't have to specify what the budget, what the borrowing constraint is. If you think about, if you were to just go look at budget constraints in the data, if you don't think anyone is at the constraint and everyone could be scaled, then you never would need to specify. You basically you need the assumption is that based on what you see, either people at the constraint, when the aggregate moves, the constraint would move with the aggregate, or that no one is actually near enough to the constraint that when you scale them, they would hit it. So we don't need to take a stand on what the constraint is, just that when we scale people, that doesn't violate a borrowing constraint.
Yeah, but how do you get agents whose Euler equation is not holding this equality?
How do we get them to fit in the theorem?
Yeah.
Well, if you scale an Euler equation that doesn't hold, the scaled version also doesn't hold. It just yeah. So that it just cancels out on both sides. So the people who are off the Euler equation, that's no problem because you scale when you scale it, they'll still be off the Euler equation.
I
Yeah.
had kind of a similar question. Can I think of the delta i's for the people who are not on their Euler equations as capturing the Lagrange multiplier on the borrowing constraint?
I mean, I think if you're at the borrowing constraint, you're consuming all your resources. So I'm just going to scale your resources exactly by what I would need to get your consumption to move up by kind of the same percent as the rank. So it's not going to be related to the multiplier. There, I mean, for those people, it's kind of the easiest because I don't need to care about the future terms.
Instead of an equation, you have a budget constraint.
Yeah, you just have the budget constraint.
But you have to assume that they don't change status. They don't go from constraint to constraint.
Yes, yeah. So yeah, so that's why. So it could be that you're going to be changing status, but it can't be that in response to the shock you're going to change status. Or well, when I kind of it's whatever your status would have been absent the shock, then I'm going to scale you so that you stay. So either a budget constraint 0 is fine, or as long as if we scale the budget constraint, then everything is allowed to go through. This is good to kind of clarify because I did sweep it a bit under the rug, but that I didn't mean to for that. Okay. So what am I going to do now? So this is kind of to the discussion with Adrian. So if we have a rank model, you can compute kind of these aggregate implications of redistribution. Kind of impartial. When I say impartial equilibrium, I mean like given rank prices, I can compute this consumption correction. The next step is how can we go from partial equilibrium to Hank GE? That's going to be the big step without adding additional information than anything we've used at step 1. then given that, we're going to kind of show you, what's the right rank model to use in order to be able to think about estimating a Hank from the data. I'll show you kind of how to do that, and then we'll do counterfactuals with this estimated model. That's the plan. Okay. Now we're going to move and think about doing things to first order. The theorem holds kind of non-linearly, but now we're going to think about kind of first order experiments. So, I'm going to kind of think about things in sequence space. We have, one-time innovation to the nominal interest rate. We'll also think about TFP shocks and compute perfect foresight responses back to steady state. So think about this as a linearization. Just to kind of complete the model, we're going to just close this kind of in the standard way of like the canonical Hank model. We're going to have, monopolies of competition, sticky wages, capital production with investment adjustment costs. We're going to have just a mutual fund that's going to hold kind of all the assets and kind of just a standard government budget constraint with these non-valued government expenditures and also transfers. And we're going to have long-term debt in steady state so that we don't have kind of big impacts of interest cost moving in response to shocks. Okay. When you get the perfect foresight response, this is kind of to the kind of the question at the beginning. We basically get this system of kind of perfect foresight equations for rank. The only difference between rank and Hank is that this block is now different, right? I mean, in rank you have an Euler equation. In Hank, all the other equations are the same, but this comes from the distribution and how people respond. So that's going to be basically we're going to say how you can kind of go from this type of equation to getting this piece, but then otherwise, kind of all the machinery that we're going to use is the same as you would use to estimate a rank model. We just need to do a couple extra matrix multiplications, and then we're there. So let me just show you that this works kind of in PE. So let's just take a rank model, something like you could take Galli chapter 3, compute the impulse response to a monetary shock, though actually it's not Galli chapter 3, it's the model I just showed you. But compute the impulse response to rank. Then what I'm going to do is I'm going to take these, from an incomplete markets model, I'm going to take the steady state distribution. I'm going to use that combined with these impulse responses in order to get the deltas. And then what I'm going to do is I'm going to aggregate these transfers using the IMPC matrix from the Hank model to get this delta C correction. And then I'm going to compare that to actually solving kind of the Hank household block at the rank price system with the deltas. So the theorem implies that, consumption and rank should be consumption and Hank given rank prices plus this consumption correction. The rank model is going to be in yellow. If you solve Hank with rank prices, you get this kind of red. If you add in kind of the delta times the MPCs, which is this blue line, you recover rank. So basically giving the heterogeneous agent economy rank prices plus the transfers, you get back to the rank impulse response. So the lines effectively coincide, the procedure works, but obviously we're not really interested in yellow, right? We're interested in red, because that's kind of what we think the DGP is. So the question is, we need to recover the yellow so that we can estimate the red. So to do that, we will also want to go to GE. So I'm going to call this like a one-shot correction to consumption, because I'm just going to take the representative age of consumption and I subtract off this consumption correction from the deltas and the MPCs. So let's call this the one-shot. So if the prices were the same, then the GE and PE would be the same. Things coincide, everything holds. But full Hank GE is going to change kind of prices and incomes, right? Kind of obviously, if you see that it's going to move things around, that's going to change prices and incomes, and that's going to have feedback. Now the remaining gap, it's not going to be something that we want to undo with deltas. That's something that we want to try to kind of capture what the feedback is, because earnings, transfers, asset cash flows, returns are all going to move. So what are we going to do? So the idea is we're going to kind of import from IKC is that you can think about this one shot as kind of like the PE first round correction to consumption. Then, we needed IMPC matrix to get this, so why don't we just use, again, the IMPC matrix to apply that to how incomes change in response to this movement in consumption. So C hat is the object that, kind of the Hank GE that we'd like to get. the income system is going to move kind of based on the full system of equations as we move that C hat. So we need to think about how incomes change relative to what they were just in rank. And we have this Jacobian from, those incomes kind of multiplied by NPCs loaded by the different incomes. So that we can kind of directly construct. Now the last piece is, we have return feedback. And for what I'm going to show you today, we're just going to close that actually with kind of the compensated return Jacobian from the rank system. So that's going to be an approximation, because this should be from the Hank system. But this is something, that kind of we don't have. I mean, this is NPCs we kind of know how to measure. This one is harder to measure. And so, this part we can get from things in the data. The return feedback we're going to kind of take from rank, and I'll kind of show you how well that does. So what's the kind of the remaining error? So the error between true Hank GE and what we would get from here is basically depends on how these compensated returns between Hank and rank differ, and also how the return paths differ between Hank and rank. So if you have like a constant R monetary policy, RH and RR are the same. And so this term drops out, and then you get everything's exact. If the real rate is the same between the two, so that's kind of beautiful. Or if these Jacobians are kind of the same, which we think, not necessarily that they will be, then again this term would be small. So we still haven't recovered the full Hank GE, but I'm going to show you that this error, at least in practice for kind of parameters and models we've looked at, turns out to be small. Which we think is mostly because, in the end, this gap ends up being small in most of the models that we've looked at. So the left panel is just saying, if I feed in kind of the same real rate path between rank and Hank, then this procedure kind of exactly gets the Hank GE. So from rank plus transfers plus this closure, we get it back. If we have kind of a flat Phillips curve, which is actually 3 times steeper than the Nakamura-Steinson estimates, but there, the inflation and real rate gaps between rank and Hank are quite small. So this, this term between RH and RR is relatively small, and so we basically get we recover very well the Hank GE consumption response. And this is also informative, right? This kind of tells us how big this GE return channel is in if you estimate on data in the real world or kind of in our models. Okay. So hopefully I've convinced you. In partial equilibrium, the theorem is correct. We can kind of recover this correction. In GE, this is very accurate when the return movements between rank and Hank are kind of not very big. And we kind of have this, we have this closure. But this is again like the discussion I've been having with Adrian is that given rank we can construct Hank, but the data are generated by Hank. So how can we get the rank that we need to construct Hank? So this is now where we're going to have this iterative procedure where we estimate a latent rank. I mean, the theory goes one direction. It would have been nicer if it had gone the other direction, and we wouldn't have had to do this. But the theory is what it is. So what's the basic idea? So now we're going to get into how to do this estimation. We're going to do Bayesian IRF matching. So if you have questions on this, ask Sean, because that's, or ask Jesus, who taught Sean, if his questions are wrong. Answers are wrong. No? Sure, fine. I see. Okay. So let's think about psi naught is going to be our baseline shock and policy environment. So this is going to, psi naught is going to be the thing that we're going to think about for counterfactuals. What we want is, we want to kind of match here a vector of Hank impulse response moments. So think about, we have impulse responses that are generated from the Hank model with some vector of parameters theta naught and under some policy environment psi 0. So how are we going to go about doing this? What we're going to do is we're going to estimate the parameters of this latent complete markets benchmark. So the parameters that would matter for rank. Then what we're going to do is for each candidate parameter draw, we're going to construct the heterogeneity adjusted model moments. I'll show you what the exact steps are on the next slide, but it's kind of what we've talked about. And so the idea is that these heterogeneity adjusted model moments are the ones that we want to match to the data, or the DGP here, which is the vector of Hank. So kind of we pick parameters, we solve a rank model. From the rank model, then we kind of recover the latent rank Hank model, and we match that to the data. So the idea is that, we kind of take the household budget sets. Here we're not going to estimate the fiscal rule, but we could do that. And the IMPC matrix, kind of as things that we could measure in the data, that just need to be fed into this procedure.
Sorry, sir?
Yeah.
Just to maybe compare this with like the jump sums paper and the IRF matching estimation is kind of done there based off of a Hank model. So what is it exactly I'm not specifying here that I'm specifying there? Like if I'm understanding it right, so the non-HA block, that is kind of still like parametrically specified in the same way. Now on the HA block, the consumption function itself, I guess the full IMPC matrix is specified, like we can
need
from the data, but then the MR or whatever, that part is imported from rank.
Exactly. MR is imported from rank. Yeah. So we need, basically what you need is you need to know what the cross-sectional distribution of budget sets look like, and you need to know the and the corresponding IMPC matrix. So to the extent that we can see budget sets in the data and we can estimate IMPCs from the data, we should be able to just have those two pieces kind of directly from the data. So here I'm going to take them from like the underlying Hank model as if I could observe them. So that's going to be, the full structural equations, we're going to have the same requirements, but these two we're going to try to just take from the data without specifying how those are generated.
And in this model, there's capital gains too, so you need to know the response to capital gains.
Yes. So yeah, there's a gamma R0, like R post in the first period also.
You count that as part of
Yeah, that, yes, yeah. Okay. So we're going to do two shocks just because, as you know, with just the monetary policy shock, sometimes it's hard to separate Phillips curve slopes with Taylor rule parameters. So if we have a demand and supply shock, that's going to give us additional variation. So, what's the procedure? Essentially, the procedure is what you would do if you were estimating a rank model with, again, just a couple extra matrix multiplications. You draw the vector parameters, you have the policy vector. That's you solve the rank model kind of in the standard way. Then you're going to construct the transfers, which is just the mapping from the rank impulse responses and the budget sets to get these deltas. Then, you multiply matrix multiplication, the deltas times the IMPCs. That gives you the difference in consumption. That's going to give us this household consumption equation. Then we do the closure that we talked about before. So kind of solving the fixed point on this to get the closure from income and from the return. Then that gives us kind of this closed Hank consumption response, which we feed back into this system. So we kind of drop the Euler equation from the rank system. We give it just a vector of consumption and then solve the rest of the system in the same way. So there's like two matrix multiplications, a matrix multiplication, a matrix inversion for the closure, and then the standard thing again. That's the basic idea, and then we evaluate the likelihood, and everything else from there is standard. Okay. What we're really interested in this for is we think this is like, a semi-structural way that we can also still do counterfactuals. So I'm going to show you a bunch of counterfactuals in like the last 5 minutes that I have. The metric I'm going to use kind of for success, or for what I'm going to show you, is I'm going to think about kind of measuring the distance between kind of whatever statistic I have at the counterfactual policy, kind of relative to the truth, given a vector of parameters. And I'm going to do this for kind of the true model, for this kind of latent rank Hank model evaluated the true parameters, what kind of this feasible one is at the estimated parameters, and then kind of a misspecified rank model. And I'm just going to normalize kind of the difference between the other model's gap and the truth divided by kind of what the true policy effect is, right? Because if the true policy effects are very small, then we kind of want to put these on a normalized footing. So just to be clear, when we evaluate the latent rank out of sample, we're using kind of the estimated parameters. We have to reconstruct the deltas, but we're not, we're not kind of re-estimating any parameters in order to do this. We're just kind of taking the equations as they are. We're taking the delta mappings as they are and just solving the latent rank model. And this is kind of saying, we do this estimation of kind of the misspecified rank to see, maybe the misspecified rank can match the data, but it's not clear that it could provide accurate counterfactuals. Okay. What are we going to think about? We're going to think about things that, counterfactors that people at central banks and policymakers think are important. You know, how should we think about setting monetary policy in terms of responding? How strongly should we respond to inflation? You know, should we be very quick in responding in terms of inertia? Should we have a dual mandate or not a dual mandate? Some countries do, some countries don't. These are the kind of counterfactuals that I think people care about the answers to, and they care about how heterogeneity is going to change the answer to those questions. And I'm going to show you that kind of we can do all these things. You know, how should you do the fiscal adjustment in response to a shock? You know, should you be running deficits, balanced budgets? You know, we can see how well we do in different scenarios there. And the kind of interesting question, we can kind of look at just a deficit finance transfer. And I'll show you this works kind of both for monetary shocks and for TFP shocks. So here's kind of the first result. So, you know, how hawkish or dovish should we be? So this is just showing, this is the impact consumption effect, and this is the cumulative consumption effect. Black line is going to be the truth, so solved in the true Hank model. The blue line is going to be the latent rank evaluated at the true parameters, and the green is when we run our estimation of latent rank, evaluating those counterfactuals at the estimated parameters. And so, you know, here you can see that, you know, we do very well. I mean, at the 1.5, that's the, you know, that's where psi equals psi 0, so that's 0 by construction. But we do kind of a very good job of capturing, you know, kind of what this cumulative policy effect is in response to changing the Taylor rule. If you do the same thing with rank, rank misses it. And, you know, these, you know, here it's kind of like a factor of 10 difference in terms of the cumulative consumption response. So rank would say, you know, consumption moves maybe like by 0.01% versus 0.1%. So rank, you know, rank can match the data, but then it's going to fail kind of spectacularly when you want to do counterfactuals. We get basically the same result for the TFP shock. Again, Hank does well, rank doesn't do well. For thinking about how aggressively should we respond to monetary policy shock, this is kind of the inertia parameter in the Taylor rule. Again, we do very well, and you know, here we start to get, you know, kind of the difference between rank and Hank is like a mild recession. You know, so it's kind of a 1% of consumption difference is how kind of off you would be in making your predictions from rank relative to Hank. You know, this is kind of the dual mandate. You know, we do again very well, and if you were to put in a dual mandate, how much more kind of contractionary would it be? This is the kind of the 80-minute question, the deficit finance transfer counterfactual. Obviously, you know, in rank, the first round, you know, nothing happens because of Ricardian equivalence. But here, you know, we get, you know, kind of almost exactly the path in response to the truth in this model, because, you know, we get the first round from feeding in the deltas from just the change in the budget, and then the closure works pretty well up to that kind of return differential. And lastly, this is just kind of showing if you were to go from running a balanced budget to, like, you know, kind of having slow closure of deficits in response to a shock, kind of black shows the truth, kind of how consumption would be different if we kind of move to a balanced budget relative to blue, which is from the model. And again, these are all kind of equivalent in rank, so there would be no effect. So we think that this is like a good laboratory to answer lots of questions that people would like to know how kind of heterogeneity changes the answer to these questions. In the last minute, the estimation recovers parameters very well. Of course, the rank parameters, it can match the data, but they end up being biased. So in my last minute, I just, you know, I think the takeaway is that we've kind of developed this model light, or at least on the household side framework, that we think is a candidate to kind of replace the heterogeneous household block with measured redistribution and income propagation. That, you know, this methodology can let people kind of do measurements, so see how important are incomplete markets for giving us something different from rank. But I think, you know, the more interesting thing is that now, you know, we can do kind of Hank relevant counterfactuals from just this estimated rank benchmark without having to kind of fully take a stand on what exactly is the household block that generates the steady state that we see. So thank you very much.
So the next paper is Gianluca. More heterogeneous.
More. Not as heterogeneous as this one, a little bit less.
Which means that we pick heterogeneous papers.
All right, thank you very much. All right.
Thanks to the organizer for the invitation to the group. The paper is joined with 3 co-authors, 2 of which are here, Matthew and Francois. They're sitting right there. So the paper has a normative angle, as you can tell from the title. And normative analysis in heterogeneous agent incomplete market models typically solves for Ramsey policy with commitment and constrained efficient allocation. There are some examples here from the literature. Now, both of these benchmark has some limitations. So the Ramsey policy is obviously a classic benchmark, but it relies on a very demanding assumption about the full commitment. The constrained efficient allocation is the ideal benchmark, always useful to compute it clearly, but the implementation is typically quite demanding in terms of instruments, because the instruments you need to decentralize the constrained efficient allocation typically are, they are maybe history dependent or not so realistic, quite complex, so to speak. So the next natural step in this literature, we think, is studying optimal policy without commitment, which is an approach that is more realistic and is more relevant for policy design. However, a full characterization of this problem is really absent from the literature because this is considered to be a very hard problem. There are some examples here and there that fill some gaps, and the paper, we think, takes a further step in filling this gap. Hopefully a significant step. You'll be the judge of that. Let me give you a quick overview of what the paper does in practice. So we're going to develop an analytical tractable version of the Ayagari model. This is a model that my co-authors have worked with, and other people in the room, like Florian and others, have worked with. And we're going to use the model to attack a classic public finance question, which is the optimal size of the government. Basically, the financing of the public good with distortionary taxes in an economy with endogenous labor and endogenous capital accumulation. It's basically the heterogeneous agent, incomplete market counterpart of the question addressed by Klein, Krusell, and Rios-Ruhl in the representative agent model. So the main contribution of the paper, we think, is a transparent characterization of all the forces that shape the time-consistent public policy. But we also have an empirical section at the end where we show some cross-country evidence on the impact of a permanent shock to wealth inequality on the fiscal system. And we're going to look at a permanent shock because we're interested in comparative statistics across steady states. And we're going to show that after the shock, spending falls, transfer rise, and the labor tax rises to close the fiscal gap. And the model simulation of the time-consistent policy agrees with these dynamics, with the data, unlike Ramsey or the second best, okay, which we think as a sign, as a sort of signature that it's a useful way to think about Markov policy, or in general, time-consistent policy is a useful way to think about the data. Okay, that's kind of what we do. So let me go straight into the model. Okay, so the model is going to be written in discrete time, no aggregate uncertainty. The economy is populated by a continuum of families, and each family has a continuum of measure 1 of members, or I'm going to call interchangeably members and agents. Agents are infinitely lived and discount the future at a factor beta. And they're going to be, in these economies, there are going to be 2 islands. Okay, think of these as being, California and Mississippi. In California, labor productivity is high and capital productivity is high. I'm going to denote this by Z and epsilon respectively. In Mississippi, capital productivity is low and labor productivity is also low. Agents are going to transition across these productivity states or islands with some probability. So that's the idiosyncratic income risk that's going to be uninsurable. And there's going to be, because of the lack of aggregate uncertainty, a stationary measure of agents on both islands that I'm going to denote with mu R and mu P. I'm going to use R for rich and P for poor, for the two islands. Period utility for each agent is defined as a function of private consumption, labor supply L, and the public good with standard properties. Okay? In particular, we don't need any assumption on separability across these 3 arguments, although if it's easier, you can think of that as being separable in 3 arguments. For the presentation only, again, this is not an assumption that we need, but just for the presentation to light up notation a little bit, we're going to assume full capital depreciation. But everything I say today goes through with the partial depreciation. Production technology is as follows. So the economy uses a production function f, which is constant to scale with standard properties, to produce investment, so basically capital next period, the public good and private consumption, competitive input around to markets, and the final good is the numeraire. The first restriction is on financial markets. So we're going to assume that households can trade in claims to physical capital, subject to no borrowing. And the government is going to choose public spending, okay, which I'm going to call kind of the size of government public spending, and taxes. And we're going to basically consider lump sum taxes or transfers, a labor tax, capital tax, and consumption tax, okay, subject to a budget constraint. That's kind of what the problem is, what the environment is, excuse me. Now, a few things about this last bullet point. So first of all, I am, in most of what follows until the very end, I'm going to think of a government that chooses one object, basically public spending, and finances with one tax. Okay, so it's going to be kind of a one instrument problem. Then later I'm going to generalize it to two instrument problem. We have flat taxes, okay, but the problem, the system allows for progressive taxation because we have lump sum transfers, and there's no public debt. Okay, we can easily relax the first two, so the multiple instruments and the kind of the flat taxes. The third one, public debt, is really sort of we think like a different paper because it kind of raises some other issues. All right. So let me now talk about individual decisions and what the family planners do. So each family planner and each individual take prices as given because they measure zero. By a large number, each family has the same share of agents on each island. Agents choose labor supply and consumption saving in every period. Now, the key assumption that makes the environment tractable is the following. We assume that the family planner can use lump sum transfers, which they have to be indexed to the individual origin island, so individual kind of initial state, and to aggregate capital, to redistribute across its members, but total within island transfers are going to net out to zero. Okay? So this is basically the assumption that we make that leads to full resharing among family members within the island and no trade across islands. And then under some parametric restrictions, turns out that the agents, the poor agents are credit constrained, and the rich agents are on another equation with precautionary saving, because there is still this idiosyncratic risk of being sent to like different islands next period. Okay? So what does it buy us? It buys essentially that inequality is only due to the current z and the current epsilon, but all the past history is erased by the full insurance. And basically that the end of period wealth distribution, because of 1 and 2, collapses to 0 and k, then I'm going to use k for aggregate capital, basically, which is essentially the capital that is held by the rich. Okay? So the distribution basically collapses to 2 points, which means that for what follows, we can only keep track of aggregate capital k as the endogenous state variable. Now, the other reason why we like this, besides the fact that you will see the environment is tractable and the equations look like the ones in basically in the Ayagari model, is that there is this very useful theorem by François and Xavier that proves that as the number of islands grows large, this island economy converges to a conventional Ayagari model. So, you take the limit as islands increase and you get to the Ayagari economy.
Gianluca,
Yes?
is K liquid or illiquid?
K is liquid. K is liquid. K is liquid. You can eat basically K and consume it, and every period.
But can you take it to the other island? When you're R, can you take it to the...
Yes.
So really the question
In fact,
is,
yes.
if you have many islands, you have different Ks on each island, or is it the same?
Yes. No, you have different Ks on each
So
island.
it's Ki,
Yeah.
and there is a distribution.
Yeah, there is a distribution. Yeah, distribution which is as the size of the number of islands. Exactly. Yeah. So let me talk about the basically. Excuse me, I skipped something. Let me talk about the government problem. So So the government is a benevolent government that maximizes welfare. This is the period utility of the government, which is basically an aggregation of individual utilities weighted by welfare weights alpha. The individual budget constraints for each type I post family planner redistribution, okay, post this kind of scheme that the family planner does, looks as follows. Okay, so you know, the budget constraint is pretty standard, except for two components, I would say. So theta is an object which is the product of capital productivity and the share of rich agents that move to island I, okay? Which is also the probability that a rich agent is gonna move to island I by the law of large numbers, okay? And you know, this is the reason why theta multiplies k, because the only ones who save are the rich, and the rich carry their capital into island I, depending on whether they go to the rich or the poor. The second part that is important in this budget constraint is the last term in blue, which is active only for the rich agents, which is the choice of capital next period. All right. Then we have household optimality conditions, which are standard. This is the standard intertemporal first order condition for every agent, and an Euler equation that looks like the standard Euler equation with, you know, an expected marginal utility of consumption next period, as in, you know, in the Kanoi-Yagari model. You have firm optimality that sets wages equal to marginal product of labor and the interest rate to marginal product of capital, and then you have a standard budget constraint. Now, I wrote this problem in general, but you know, later, what I'm going to do, I'm going to focus on the analysis of a planner who chooses G and is going to finance G with the labor tax. Okay, so when I go to the solution of the planner problem, I'm going to focus on this case, and then I'm going to talk about the other cases later. Okay, very good. So let me tell you a little bit about time consistency now that we have the government problem. So as you know, the commitment solution is time inconsistent because it's a classical problem. The capital is elastic today, but it's predetermined tomorrow. So that changes the incentive of governments who cannot commit. Now, we're going to rule out commitment technology, which means that the government sets the current policy and takes the future policy rule as given. Okay? So we're going to use as equilibrium concept the same equilibrium concept of KKR, of Klein-Crozer-Rose rule, which is called a differentiable Markov perfect equilibrium. So it's Markov because policy rules and decision rules depend only on current payoff relevant states, all the current payoff relevant states, which in general with the distribution here is the aggregate stock of capital. It's perfect because there's no profitable one-shot deviation by the government. And it's differentiable because basically we're going to work with a model where all the policy rules, I mean, all the decision rules and the policy rules of the government are smooth, essentially, which allows us to take first order condition and characterize things in terms of first order conditions, but also it's a form of equilibrium selection because it basically rules out trigger strategies, which can lead to other types of equilibrium, which might have higher welfare, but it's a sort of a different family of equilibrium, okay? So we're going to rule them out. In terms of methodology, we're going to use a perturbation method, essentially, which is going to lead to a generalized Euler equation for the government, and which we're going to try to characterize in closed form. That's kind of the want operator here. So how do we construct the Markov perfect equilibrium? So the key objects are a government policy function, okay, psi of k, and household strategies, which are the script H and script L. And basically the problem becomes a Stackelberg game in which the government chooses G for the current period, taking as given the rule as a function of capital stock next period. And private households follow with choices for their own labor supply and their own capital, their own savings, essentially. Now, to construct the Markov perfect equilibrium, you use the so-called one-shot deviation principle. So you check, basically, that there is no k at which one period deviations for the government to set G different at a given k, to set G different from the psi of k, the policy rule, would be profitable. Okay? And in order to do that, basically, you have to define these one-shot deviation functions or household responses. Okay? So H of K and G is going to be the function that describes the saving decision of the rich if today's state is K, current government chooses G, and the future government follows the rule psi. Okay? So basically, you allow the household to change their saving decision if you choose a different G from psi of K. And similarly for the labor supply response. Okay? Now, notice that if you evaluate H of K at G equals psi of K in equilibrium, you're going to recover the individual policy, individual decision rule, and the same for the labor supply. All right. So that's the equilibrium concept and the construction of the MP. Now what you do, you basically write a recursive formulation for the government problem, okay? Where this is exactly the slide that I showed you before, but written recursively, where everything is a function of K and a function of G. Now, this is a bit complicated. It's a bit dense, this slide. But fundamentally, it's there because I want to show you a couple of things. The first is that, everything basically becomes a function of G. Okay, not everything, but most objects. The policy function, the decision rules, the aggregate labor supply, the tax function that you derive residually from the budget constraint and so on, a function of G. Okay, so here basically what you do, you write down the problem and you take a first order condition with respect to the dynamic problem of the government, and you have to differentiate everything that depends on G. Okay, and then you stare at the first order condition, you try to combine terms and to make sense of what you get. Basically, that's the other thing that I want you to notice is the following: that the terms that I highlighted in blue. So here, the government takes as today does not commit, right? So I cannot choose future path of G. So takes as given the policy rule of the government next period, but understands that by choosing G is going to affect the saving decision, okay, this H, and therefore the argument of the policy function. So it can affect the behavior of the future government through the argument of the policy rule, not through the policy, but through the argument of the policy rule. Yes?
So if you wanted to do this in the original Ayagari model, would these equations basically be the same except the K would be the super high dimensional thing, and
So-
the H would be high dimensional, but like,
Yeah.
why do you need the item thing to just write this down? Like, then there's a separate question of solving.
No, I could write this in the general model. I could write, up to this point I could write in the general model, okay? And then I could say, okay, now I'm going to make this assumption, and to this assumption I can get some closed forms.
Right.
And the closed forms are coming. So
Oh,
that's where
from
the,
closed form.
yeah, the closed form.
But even
Closed,
maybe
yeah.
just the feasibility of it, because it's
Yeah, no, we solved this model for a case with 7 islands, I think, and like a large number of islands as well. And we get very similar results in terms of sort of qualitatively, and even to some extent quantitatively, what this policy looked like. But then, there is sort of a computational feasibility of the number of islands you can keep track of. So because the aggregate state vector is basically the initialization of the island. So yeah. But yeah.
Are you gonna talk through the economics of the Stackelberg thing that these guys are engaging in?
Yeah, I will in a couple of slides. I will start talking about the forces that shape the optimal policy. This is just to set up the problem, make you understand the way we solve it. Absolutely. Okay? So in fact, I'm going to go to the characterization in one slide. Let me just define a Markov perfect equilibrium formally. So a Markov perfect equilibrium for this economy consists of and this is general, of a government policy function psi of k, a government value function v, and household response function h. This is basically the what leads to the aggregate capital stock next period and individual labor supplies, such that psi is the solution of the government problem which is this dynamic problem here. V is the value function of the government that satisfies this recursion. Okay, where this is K prime, which is generated by the one-shot deviation function of the household sector. And for all K and G, H and L are implicitly determined by the Euler equation and the intertemporal first-order conditions. So these this set of equations here. Okay, the H and L basically are the ones that satisfy this system of equations. Okay, good. So let me now move to the characterization. Okay, so here's the planner first-order condition. I mean, let me just show you the value function of the planner again, which is this value function here. So you take first-order conditions with respect to G, and you obtain this planner first-order condition that basically equates the marginal benefit of a unit of public good to the marginal cost. The marginal cost is the marginal utility of consumption today, plus the fact that, you know, if you supply one extra unit of the public good, you have to tax. If you tax, you're going to reduce savings. That's what this H of G is. And if you reduce savings, you're going to reduce capital next period, which is valued this way by the marginal value of capital next period. Okay, so that's kind of the first order condition of the plan. Now, if you use the envelope condition and you do a few additional steps, you can substitute the V prime of K and you obtain this equation here, which is the generalized Euler equation. Okay, that's the generalized Euler equation for the government. Now, I explained what this term is. These are just derivatives of the current welfare with respect to G and K. What is this term here? Well, the way to think about this term is to think about basically the H function forward one period, okay, updated one period, and then if you take if you differentiate this function by setting d of k double prime to 0, you see that basically what this term is the effect that the savings next period has on the choice of G next period, basically. Okay, so that's what this term captures. So overall, basically, you can get to this interpretation of what the terms mean. The first term is a static term that captures the effect of the public good through taxes, through today's taxes, on current welfare. The second term is the first dynamic term that captures the effect of the public good through today's taxes on savings, and then through savings on welfare. The last term is the effect of the public good through taxes today on savings, and how savings affect G next period, the provision of G next period, and these through taxes, how it affects welfare next period. Okay? So these are basically the static term and the two dynamic term that enters the generalized Euler equation, and I'm going to tell you basically what these terms look like and what forces they capture. It's useful to begin from the static term, from this W sub G, which is the static term. So in fact, let me make an assumption, okay, to isolate the static term, that beta is equal to 0. Okay, so there's no future. We're in a static economy. And, you know, it's useful to start from a very simple case, which is kind of a textbook case. No income effects on labor supply and G financed by lump sum tax. Okay, that solution yields the celebrated Samuelson rule, Samuelson 54. That basically states that the average marginal utility of the private consumption is equal to average marginal utility of the public good. Okay? So I'm going to call this gap here the Samuelson residual, SR, for the Samuelson residual. Now, we're still in the static model, okay, so no capital. With endogenous labor and distortion and tax instrument tau, one of the ones that I showed you earlier, the Samuelson residual is not 0 anymore, because taxes now are distortion, so they have consequences. The first term that shows up is basically distortions to labor supply that affect the tax base. I'm going to call it B. The second is a direct distribution of income across types via taxation, that I'm going to call R. And the third is this indirect distribution of income through prices, basically through wages, that occurs in general equilibrium. So we can show, in fact, that the Samuelson residual is the sum of these three terms in general in a static economy. And let me tell you how these terms look like. This is where you start seeing kind of the payoff of the sort of the tractable model. This term is the tax-based term. Okay, so if you stare at it, you see that if distortions reduce labor supply, so NG is negative because IG like taxes, NG is negative, then the tax base shrinks, and this term is going to become negative, which leads to less G. Let me just remind you the way I wrote the Samuelson residual so that you, okay? I wrote the Samuelson residual this way, so you have a minus average utility of G, so that basically an increase of this means that G goes up with a minus sign, okay? All right. That's the first term. It's kind of the fiscal externality term. The second term captures the following. If the poor agents, which are the ones with high marginal utility, have less labor income than the rich agents, so this inequality is true, then direct distribution through labor tax goes kind of the right way from the point of view of the plan. Remember, this is an economy with incomplete markets where you want to redistribute, and the distribution goes the right way. So R is positive, and this leads to more G, because by taxing, actually the distribution the right way, so you like that. The third term is the distribution through prices, through wage that occurs in general equilibrium. So if taxes reduce labor supply, say as a kind of intuitive, and poor agents with high marginal utility, they have larger share of labor income than capital income, so this inequality holds, then indirect redistribution goes also the right way, because you're reducing labor supply, you're increasing the wage, and the wage redistributes more towards the poor people, okay? So these are the three effects, basically, that shows up in the static economy. Tax base, direct redistribution, and equilibrium redistribution. Two notes. First one, the representative agent is a special case of this. With the representative agent, clearly this term is 0, because this is 1, and this term is 0, because these are also, they're 1, both of them. So the only term that shows up is the tax-based term. Okay, so these other two terms are germane to the heterogeneous agent model. Second, you might have noticed there is no term whatsoever in this representation that is in the marginal utility of labor, utility of labor. Then because these terms vanish because of the envelope tier. Okay, so it's not that they are there in the background, but they basically vanish because of the envelope tier. Good. So that's the static. That's the static case. Now, we have a general representation of the static case for any of the tax instruments that are used to finance G, okay, which is here. I'm not going to go through this, but you can see that all the terms are sort of very similar to each other. I just want to point out that some piece of notation I'm going to use later. I'm going to use M for the average marginal utility of consumption, ML for the average marginal utility of consumption weighted by labor share of income, and MK weighted by the capital share of income. Okay, and I'm going to use MG for the average marginal utility of the public good. Yes?
There is no fundamental difference between the tau K and the tau L?
Yeah, there is.
How would you, I thought that it would be like radically different because of the intertemporal dimension, but it seems like, I don't know, at least so far, I guess this is only the static piece, then maybe there is more difference down the road for the other thing.
Well, yes, there is, I mean, the way to think about this MK right now in the static model is, that these thetas are the shares. Think of K as being a capital, like a fixed factor, basically, in the static model, and these are the share of the fixed factor owned by the rich and the poor, essentially. Okay. Yeah. But there's no dynamic distortion or dynamic incentive problem, which is going to show up now. Okay. So remember, this is again the generalized Euler equation. We talked about the static term, and there are these two other terms which are dynamic term. Now, this term here, W prime G, has exactly the same form as the static one next period. Okay, so all the terms show up exactly as a static term, but with a prime. The new interesting term is this W prime K, okay, that remember captures the effect that essentially G has on taxes, taxes has on savings, and then how savings affect welfare, which has these additional two terms. The first one, it looks like a tax-based term, and in fact captures the labor supply distortion to the tax base through K prime, through savings. Okay, so you provide public good, you need to tax, you have to raise taxes. Taxes, you affect savings, and savings, by, let's say you reduce the capital stock. Reduce the capital stock, say reduces wages, increases the interest rate, and changes labor supply through wealth effects, and that changes the tax base. The other term that shows up is another this general equilibrium distribution term that occurs through K prime. Okay, so this is in fact exactly the term that you have in the Davila, Hong, Cosenello's rule, if you're familiar with the paper, the econometric paper, the constraint efficiency paper. And there is this idea that basically by changing capital next period, you're changing prices next period, and you're redistributing through prices. Okay? What you want to do basically, you want to increase capital ideally to increase the wage and distribute towards the high margin of consumption. Okay, so combining terms. Also I'm going to do the case, the steady state case. Okay, so I'm going to basically get rid of the primes, assuming that you're in steady state. This is the steady state generalized Euler equation. You can essentially write once you substitute the various component, the Samuelson residual, which remember it's 0 in the benchmark economy, and it's only equal to these three terms in the static economy. You can write it sort of this way. Okay, and all these terms have a clear interpretation, and they can be easily computed. Yes.
Yes. What does it mean to get rid of the primes? Like as I understood, you had the ratio of the H's, which was related to the derivative of the policy rule.
Yeah.
And that's really where the punishment would be.
Yeah, that's right. So what I did basically, in steady state, you get rid of the primes because
You set it to 0. You said that there is no.
no, I don't say it to 0. It's not a myopic. Is a world where basically H prime K, which is HK next period, is equal to H prime G, which is the one-shot deviation function next period, is equal to the one-shot deviation function today because we're in steady state. Okay, and so you're exactly right. What happens is that this HG simplifies within H prime G. That's why there's no HG anymore in the. Yes.
Have you tried this? I mean, for a Ramsey planner, you have this equivalence with the golden rule when beta goes to 1. No? In this case, is there anything like if you maximize steady state utility instead of the dynamic problem, how would it be different from this?
I see. I don't think we've thought about it. Yeah, I understand exactly what you're saying. We have not thought about it. It's not hard, I guess. No, you can take a limit, but you have to be careful, I guess, with the. But yes, we'll look into that. So, thanks. Yeah. Anyway, so this is what the Samuelson residual looks like. And notice that all these terms, okay, they're indexed by tau L because the instruments that I'm using to finance G is tau L, okay? But we have a representation for the capital tax, the consumption tax, and the lump sum transfer, which is lump sum tax, which is the easiest case. So summarizing, basically, the Samuelson residual in the generalized order equation is determined by these fiscal externalities from labor supply, the P terms, directly via G and via capital accumulation next period, directly distribution from labor taxation, okay, just the taxes redistribute, and this indirect distribution through prices will occur via G and via taxes directly and through capital accumulation next period. So these are all the effects essentially that the planner has to take into account to think about you know, the optimal choice of G in this sort of Markov perfect equilibrium.
Would you have other terms there if you were using capital taxation?
The terms look different. You still have the same terms, but the terms look different. Francois, correct me if I'm wrong, but I think, yeah.
What? Can I ask the question?
Absolutely.
Yeah. So I thought, you know, you would have an impact on labor today, and that would be, and you would have an impact on labor today, and that would be it. But with capital taxation, you're going to have an impact on capital tomorrow as well.
Yeah, but here as well. Here, oh, sorry, going the wrong direction. It's, I mean, these two dynamic terms, they tell you exactly that if you change your choice of G, you're going to change just the labor tax today, and the labor tax is going to affect the saving decisions. Clearly, you know, to the budget constraint, to distortions, and that's going to affect the yeah. I mean, this is a general representation that doesn't depend on the tax instrument. What depends on the tax instrument is what exactly the term look like, precisely. Yeah. You can see it here partially in the static case, but in dynamic case, I don't have the general slide for the dynamic case, but okay. All right, good. So, all right, so that's all for Markov perfect, but I want to tell you a little bit about constraint efficiency because we also characterize the constraint efficient allocation. It's actually much simpler to characterize. So the constraint efficient allocation is the best feasible allocation that is chosen by a planner who is constrained by the financial market imperfections of the competitive equilibrium. And importantly, this took us a little bit of time to understand this, the incidence implied by the fiscal instrument that finances G. Okay? So you also have to constrain the planner this way to think about what is the counterpart constraint efficient to the Markov perfect equilibrium that you're analyzing. We show that actually this constraint efficient allocation can be implemented by task-specific Pigouvian wages and rebates that reproduce the planner's labor and saving historic condition without any net transfers across types or across islands, because this is what respects the constraint number one. Okay, but we show what the taxes look like, and they're also they're a bit complex. Okay, that's why, because they're type specific, so. That makes this sort of unappealing from the point of view of decentralization. But the generalized order equation is very, very clean for the constraint efficient case, because that's what it looks like. It says the sole residual, the Samuelson residual, I make this mistake all the time, all the time. The Samuelson residual is equal only to the direct distribution term, RT, okay? Because there are no fiscal externalities, there are no price externalities in the constraint efficient allocation by definition, and the tax base, the fiscal externalities are also essentially fixed by the Pigouvian taxes and transfers. But you cannot avoid the direct distribution across types. So what I'm going to do now, okay, I'm going to show you some plots. I'm going to express the generalized order equation for the constraint efficient allocation this way, okay? So I have the minus mg here, which is the average marginal utility of the public good, the average marginal utility of the private consumption, and this redistribution term, and I'm going to express this, the g in the Markov perfect equilibrium in the same way, so they are kind of symmetric. again, because you have this minus mg, I did it in a way that, if you see these terms going up on the right-hand side, it means that they push for more g. If they go down, it means that they push for less g. And the exercise I want to do, I want to tell you basically how these terms move when inequality changes, when wealth inequality goes up. Okay? Because we're interested in that eventually when we go to the data. And the bottom line, I'm going to anticipate, is going to be that basically these terms push in different directions. Some push up, some push down. So ex ante, it's very hard to tell whether, as inequality increases, a Markov perfect equilibrium planner wants more G or less G. All right. So here's a you have 6 terms on the right-hand side here. Okay, so you have 6 panels. These 6 panels correspond to all the terms. And what I do basically, I'm increasing the dispersion in the productivity of capital between the poor and the rich island to increase inequality. I do it with the productivity of capital. I can do it with productivity of labor. Do it with the capital. And as we do that, the bottom 50% wealth share, basically the wealth share of the poor, falls. So there's more inequality. Okay. So here, let's start from the constant efficient allocation, which is the simple one. There's only 2 terms. As the m terms is the average budget utility consumption. Okay. Well, there it's easy to figure out that if the budget utility is convex, you increase inequality by Jensen's inequality, the term is going to get bigger, and so it becomes as a minus sign here. That pushes for clearly less G. Okay, that's kind of intuitive, less G. But there is this direct distribution term that is also present in the constant efficient allocation that pushes for more G because it goes in the right direction. Okay, so the 2 forces, not clear what's gonna happen. It's quantitatively ambiguous. Now, for the Markov perfect equilibrium, there are a bunch of other terms, but if you squint a little bit and look at the scale, you see that the only term that is really large comparable to those 2 is this one, the indirect distribution, the dynamic indirect distribution term. Okay, so this term that tells you, well, if you screw up capital accumulation, capital is going to be low next period, the wages are going to go down, the interest rate is going to go up, you're distributing the wrong way, and the more inequality you have, the worse it is. So you want less G. Okay, keep that in mind for later. Okay, so now I want to. This is just it's from the calibrated model, but it's basically an example. I want to go to the data and try to figure out what happens to the fiscal system when inequality goes up. Okay. Here's the way we do it. So we want to try to identify a permanent innovation to wealth inequality. And then trace the fiscal system response, condition on the forces that we're not abstract from. So it's not going to be necessarily causal, because we don't really have strong cause identification, but the analysis will be informative of the equilibrium relationship between the fiscal variables and inequality, we think. Okay? So we go to the data, we select data for 38 OECD countries, 70 to 2023. From the World Inequality Database, we have measures of inequality. I'm going to work with 2, one Gini and the bottom 50% wealth share, which I like because it maps directly to the model. From other data, we get all the fiscal variables that we want, spending, transfers. These transfers exclude pensions. These are just cash transfers, working age people, and tax rates on labor and capital, and also consumption. Then, from other data, I gather, from other databases, I gather data on controls, things I'm going to throw into our local projections to control for variables that the model doesn't have, like GDP, population shares, that we think, like an aging population might affect the fiscal system, unemployment, trade openness. We also have a bunch of political variables that, because we think maybe the political system might affect the fiscal variables. The analysis is we want an analysis which is sort of low frequency in some sense, right? So all these variables might affect the dynamics. And then we do the following. So the main problem that we face is that a lot of variation of wealth inequality in the data is actually due to transitory swings, which we think are asset pricing swings, basically. But we want to isolate the permanent component because we want to do comparative statics in the model. And so we want to look at a permanent shock. So we basically, in step one, we do a permanent transient decomposition of inequality into a random walk and a cyclical component. And we extract the permanent shock, the permanent innovation through Kalman filter. And then we run, they call this S the shock, and then we run these panel local projections. We have the shock here, country fixed effect, time fixed effect, bunch of controls, the one that I talked about earlier. Standard errors that Claude tells me they're robust to spatial and serial correlation. We have the expert here, so good. Better than Claude. And we're throwing in some leads into the local projections to kind of placebos. And this is what we get. We get something that is kind of clean. So this is basically the shock, okay, which is normalized to 1 percentage point of the Welch share. I'm doing it with the bottom 50 Welch share, but the results for the Welch Gini are very similar. So inequality goes up, G over Y falls, transfers go up, and among taxes, it's the labor tax that goes up. Capital tax and consumption tax. This is really not the consumption tax, it's a residual tax. So there's some other taxes in there, but basically it's flat. Okay, so the data tells us, well, inequality goes up, spending falls, transfers go up, and the fiscal gap is financed by the labor tax revenue. Okay, so we want to try to, yes.
Is there a reason why you went for financial wealth inequality rather than income or consumption inequality?
Well, in the model there is a very close resemblance between the two because of the island model. In general, it wouldn't be the case, and I think there's a lot more temporary variation maybe in income, and wealth is really the state. So we opted for wealth inequality as well.
Yeah, so it's just hard to think what would move wealth inequality in 1 year if not revaluation.
Maybe it's like something that is more. Maybe it is a surprise movement. There are more permanent movements. I mean, I imagine that if you do like a permanent transfer composition or a surprise movement, you do find a permanent component there as well. So maybe it's that. But yeah, we should look into that absolutely. So I have 2 minutes. So I need to speed up. Okay, so we calibrate the model. Let me skip the calibration, but it's actually. In spite of the fact that it's only a two-type model, we can match a bunch of things. And so what we do is comparative static across the state. So in the model, we're going to increase wealth inequality by expanding the gap in capital productivity. And this is the new thing. Now we have the G moving, the transfer moving, and the labor tax residually. So we need 2 instruments. Okay? So we're going to resolve the model with the Gorman chooses 2 instruments. We have 2 generalized Euler equations. And that's what we do. And then we're going to compute macro equilibrium, Ramsey, and the constraint efficient allocation. And these are the results, basically. This is, as we increase the gap in capital productivity, the bottom 50% share falls, so more inequality is going this direction. And, what you see, basically, is that numeric, quantitatively, in this calibration, which is calibration of the model, the Markov perfect equilibrium is the only allocation that implies a decline in G over Y as inequality goes up. And this is related, with respect to the constraint efficient, is related to this additional term that I showed you earlier, the indirect distribution through prices. It's that pushes G over Y down. Transfers go up in all 3, labor tax goes up in all 3 to finance the gap. I think I need to conclude. So I didn't have time to talk about Ramsey, but we're looking to trying to characterize the Ramsey policy also kind of in the same way in closed form to have more intuition. So it's actually harder than the Markov perfect equilibrium. Okay, so just to conclude, we extended the representative agent analysis of time-consistent public policy of Klein, Rosen, and Rousseau, essentially, including the methodology to model the heterogeneous edge and complete markets. And we're able to derive this transparent closed-source solution for the general equation in a tractable version of the model, which I think from what we've seen from solving more complex models, you get basically the same terms, even in the richer Gary model. And we highlighted this offsetting channel that shaped how optimal policy varies with big inequality. We also documented how permanent shocks to wealth inequality affects the fiscal variables in the data, and we show that in the calibrated model, the Markov perfect policy can replicate the data, while Ramsey and also the second best cannot.
Anyway, we are going to have now the second session. Same rules as before. Yeah. Fine. Because we have fist of fire.
Okay, thanks a lot to the organizers for putting the paper in the program. This is joint work with a great team, Daniel, Davide, and Laura. Davide is in the audience today and might help me out with some questions. We're generally very excited about your feedback. The motivation for the paper is that an important way through which monetary policy affects the economy is by changing firms' investment incentives. And this investment channel of monetary policy has therefore long been an object of interest for macroeconomists. More recently, there has been a particular focus on heterogeneity in the cross-section of firms in this channel. And the literature has actually given us a lot of results. At least since Gertler and Gilchrist, we know that small firms tend to be more responsive to monetary policy. But apart from firm size, subsequent papers have linked the responsiveness to monetary policy to leverage, age, liquidity, debt maturity, types of collateral, etc. So we have learned a lot from this literature. What most, if not all, of these papers have in common is the empirical approach, which goes as follows. The researcher selects one firm characteristic ex ante, for example, motivated by a structural model, and then includes that firm characteristic as an interaction with a monetary policy shock or monetary policy surprise in a panel local projection. So we've written down one of these panel local projections here. The firm characteristic is XIT, so that might be firm size or firm age. And then I is a firm, T is time, H is the response horizon. On the left-hand side, we have investment, or the change in the capital stock. And on the right-hand side, apart from controls, fixed effects, etc., what is the object of interest is this interaction between X, the firm characteristic, typically lagged by a period, and epsilon, which is a monetary policy surprise. And then the coefficient beta captures the change in the responsiveness of investment to monetary policy as X goes up by 1 unit. Now, the point of departure for our paper is to point out that this specification tells us something about a very specific slice of the heterogeneity in the responsiveness of investment to monetary policy, and that's the X dimension, the dimension of the chosen X. But in principle, the literature has focused on many of those X's. They could all matter for the responsiveness. They're actually typically correlated, and they could all matter, interact in complicated ways. They could potentially non-linearly affect this relationship. There could be X's that haven't been looked at, or indeed there could be unobserved heterogeneity in this responsiveness. So what we want to do with this paper, our aim is to have a more comprehensive characterization of firms' responsiveness of investment to monetary policy, which we're going to be calling the RIMP. The RIMP is the responsiveness of investment to monetary policy. And instead of picking a firm characteristic ex ante, we want to try to trace the full distribution of firms' RIMPs. And in principle, the way we want to think about that is you take a panel local projection, you have the monetary policy surprise in there, and the coefficient on that monetary policy surprise ideally should vary both by firm and by time. Of course, you cannot simply have that vary by firm and time, because the data in that local projection, panel local projection setup typically only varies by firm and time. So you somehow need to reduce the dimension. One way would be, for example, to just run the local projection firm by firm. Then it would vary by firm, but it wouldn't vary over time. What we instead do is we use a clustering approach, specifically a Gaussian mixture regression framework. I'll of course go into the details of how that works, but essentially what that framework does is it takes every firm time observation and puts it in a bucket where each bucket corresponds to a RIMP coefficient. And then once you have those buckets, the coefficients for each bucket, and the probability that an observation falls into these buckets, you can trace out a full distribution. I'll of course get into the details. This approach has been used successfully by my co-authors for the household world to estimate heterogeneity in the MPC. We're applying this procedure here to firms.
So from what you described, then basically you're also allowing firms to change type.
Exactly,
Which
yeah.
is striking.
And we think this is important, first because that would be the case in many models of firm heterogeneity, where you have idiosyncratic states that vary over time, and also a lot of the characteristics that the literature has focused on vary over time. Okay, so before I get into the details, just some features of our approach that I want to highlight. So what we do is we are ex ante agnostic about what determines this responsiveness. Okay, we don't take a stance on what the X is, what the slice of the heterogeneity is. We allow the responsiveness to change within a firm over time, and we can characterize both observable heterogeneity and latent heterogeneity. Indeed, then ex post, once we have these estimates, we can then afterwards link them back to firm characteristics. So basically we can take our RIMP estimates and then ex post run a regression, run a horse race, throw in all of those characteristics that the literature has looked at, and look how much they explain. And we can do that with interaction terms, with nonlinearities, etc. So this is kind of the features that stand out about our approach. Let me preview the findings and then go into the details. The first set of findings is about just the features of this RIMP distribution. What we find is that most firms in most time periods respond weakly to monetary policy, but the response is significantly different from zero. So there isn't a non-responsiveness group. Everyone responds, but most firms in most times have a small response. Only 5% of firm time observations show a very strong responsiveness. So most firms in most times don't really respond much. They respond a little bit. Sometimes some firms have a strong response, and that strongest response coefficient is such that a 25 basis point monetary policy tightening lowers the growth rate of capital by 1 percentage point. So this is an economically strong effect.
Sorry, Thomas?
Yeah.
Just to interpret the magnitudes, what's the scale of the tightening like in dynamic terms? Because an investment's going to be very forward-looking. I would actually like to know what like the long rate movement is.
Yeah, there is some persistence in what the Fed funds rate does in response to the shock. I don't have a picture in that in the presentation here, but yeah.
Okay.
Point taken. We should plot that. Yeah. Thank you.
So, once this coefficient can change by firm and time, why is it the characteristic of the firm and not the type of shock you're facing? Like what I'm thinking is, like, suppose that if the shock is very big, then I respond differently than if the shock is small. That is going to be picked up by a ring that is large, but it's not perhaps not the firm characteristics per se. Is it something that you can study?
So we don't pick any firm characteristics here. Basically what this algorithm will do is based on the investment behavior of different firms and based on the profile of the shock, which only varies by time, not by firm, because it's a monetary policy shock, you retrieve these estimates. So yes, when the shock is big or small, that will of course matter for these estimates. But we're not ex ante linking that with any characteristic. Okay, so yeah.
Are you going to tell us more about how this 5% is like clustered over time or crises, business?
I'll show you. Okay, so we have these features of the distribution, and then we link that to firm characteristics. First, we can just split it by variation across firms and variation within firm across time. and we find that actually most of the variation is within firms across time, which we think is interesting. We then take candidate characteristics from the literature, such as size, age, leverage, etc., and regress our RIMP estimates on these characteristics. What we find there is that the direction of these of how a characteristic affects the responsiveness mostly lines up with what the literature has shown us. There are some exceptions, which I will get to. And we also try some new firm characteristics that haven't really been tried. The literature has mostly focused on characteristics you can calculate in CompuStat, but we go a little bit beyond CompuStat with survey data, other characteristics, we throw them in. But then what really stands out is whatever you throw in this regression, even as you put nonlinearities, interaction terms in there, a large fraction of RIMP, of the responsiveness to monetary policy, actually remains unexplained. Okay? Yeah, Adrian?
So the small share of large responsiveness with variation within firms, that's suggestive of like a fixed cost type of model, like a lumpy adjustment model. And so some people have tried to measure things like capital gaps, because in those models, the thing that would be most predictive of the adjustment would be how far are you from your optimal capital level.
Yeah.
Is that something that you look at?
Yeah, we are going to, a few things. We're going to link this also to structural models. I'm going to talk a little bit more about that. When it comes to adjustment costs, we try to measure in CompuStat, we try to measure things like the distance to the last investment spike and things like that. We try to construct measures that relate to that kind of mechanism. Those things mattered, but it's not like they increase the fit enormously. So we think there is something about lumpiness here, but it's different from the unconditional lumpiness in investment, because it's a lumpiness in the responsiveness, and that's kind of a distinct, related but perhaps distinct mechanism. Okay. So I mentioned it. We then draw out implications for structural models of firm heterogeneity and monetary policy. And what we want to argue is that we provide some new targets for these models. In particular, and we have kind of a case study that I will get to at the end, we take a model, a heterogeneous firm model, and we demonstrate that there are two different calibrations for which the relation between the RIMP and firm size is the same, but the overall distribution of RIMPs looks very different. So if you take a one covariate approach, that is consistent with multiple calibrations, where this full distribution can distinguish these calibrations, which we think is a nice case study. Okay, so let me now get into the details. The first thing we need to do is decide on our benchmark empirical framework. And there are some differences in the literature. We can argue about what is the right shock, what is the right measure of investment. What we do here is we basically, in all of those choices, follow the Ottonello-Winbury paper. That's a central paper in the literature, and we simply use exactly their data, which is CompuStat, exactly their left-hand side variable, which is the change in the log book value of tangible capital, and exactly their measure of monetary policy surprises, which comes from a high-frequency identification procedure. Of course, our approach is applicable to making changes there. We just want to ensure comparability and follow Ottonello-Winbury. So then we set up the homogeneous specification, which on the left-hand side has the log change in capital at horizon H. And then we have the monetary policy surprise, again denoted by epsilon m. What we want here, what our goal is to characterize heterogeneity in that lambda coefficient. I'm calling it lambda now because beta was the one that had the interaction in it. Lambda is the one on the surprise itself. So a couple of remarks here. We follow in all of those choices Ottonello-Winbury. One thing that we do not do is to include firm-level control variables, because we want to bring those things in ex post. So those things are not here ex ante. Some aggregate controls that they use are here, and they are denoted by Z. And then now what I'm going to do is I'm going to focus on the case h equal to 0. Most of our results today are going to be about the impact responses. We have results that I will also get to for the full impulse response function, but for the next few minutes I'm just going to talk about the impact responses. So this is the homogeneous specification and the data setup that we start from. What we then do are two preliminary steps. We first absorb the firm fixed effect, which is in the Ottonello-Windry specification, and we residualize everything with the aggregate controls. So we regress left-hand side and right-hand side on aggregate controls. Though that we do these steps first as preliminary steps, that's innocuous for what you do, for what we do, but that's how we proceed. And then you get that specification. Everything that has a tilde on it is after we absorb the fixed effects and regress on the aggregate controls. So we have those tilde terms, and then now we set up this Gaussian mixture regression. And the way this works is that there is a finite number, big G, of lambda coefficients. G is going to be a choice, but we can determine that in a statistically optimal way. I will get back to that later on. So there's a finite number G of these lambda coefficients. And then there's an indicator, a dummy variable, that basically assigns every IT pair to one of those lambda G coefficients. Okay, so there are big G different groups. Each group has a different lambda. Yeah.
I thought that in the Merchangeton paper, the assignment was probabilistic.
Yeah.
It's deterministic.
No, it's probabilistic.
Oh, sorry,
It'll become clearer, I think, when I get into the
There's a
procedure.
function there. There's a 1, 1, 0.
Yeah.
So this is the data generating process, and then the estimation, you estimate the posterior weight.
Ah, okay.
It's gonna,
I see.
you'll see it.
I see.
I think it will become clear in the
Okay, so
next slide.
So this is two
Yes,
of the work.
perfect. I understand it. Yes, yes. You're thinking about in the world, every firm and every T belongs to one time,
Exactly.
but then we cannot determine that exact. So we're going to. Okay.
Yeah.
Perfect.
Yes, please.
So I just want to make sure I understand the frequency. So the surprises are super high frequency, right? And what's on the left-hand side is what, like a quarterly book value
Yeah.
in CompuStat.
Yeah.
So my H0 is that the coefficient should be 0. I have no reason
That-
to believe that the book value that lands in CompuStat in this quarter should have anything to do with like the tiny surprise window FFR thing that half an hour before an answer gets received.
That's how the literature does it, and it finds big effects. But this is sort of a.
But you guys do it better and you find that it's mostly 0, as I understand. So I'm not quite sure what we're trying to explain, because. But anyway, whatever. Just it seems a bit.
Yeah, I mean, maybe that's a
for too long, probably.
that's a discussion for later in the day, maybe. Okay, so how yes, please.
So if I understand correctly, then your group is perfectly synchronized between in terms of volatility of this, idiosyncratic shock at IT and sigma G captured by sigma G, and also the parameter like lambda G. So they must be the same group, right? So if you have like a high volatility form, then they must be systemically,
Yeah, the sigma is G specific.
Yeah, so sigma is also G specific, and lambda is G specific, but they are the same G. So when they move all together.
That is correct. Yeah.
Is it at all restrictive or is it supported by data? Because the lambda G is like more difference in terms of systematic response than the, sigma G is just purely idiosyncratic part.
Yeah.
We need the parametric assumptions for the estimation. So.
But I guess you can put the two structure for two membership, two groups, like wouldn't be that like burdensome, right? You have like, for instance, 4 groups for lambda G and then 4 groups,
Yeah, we haven't done that. I guess that if there was really a two-sided dimension, then our optimal choice of G would pick up a larger number of G's, where some groups have the same lambda in different sigmas, or vice versa. But we should look at what you're suggesting.
Okay, so let me show you how the algorithm works. So there is a distributional assumption on the error term here, which is normal. So what you can do for this specification is to write down a likelihood. So we first do that. This is the likelihood for the problem, where phi is the standard normal PDF. And what you have in this likelihood is the data, the parameters, but then you have pi g, which is the unconditional probability that a distribution will fall into group G. And you have this indicator variable dg. I should have said, sorry, now to simplify things a little bit, we're calling an IT observation a J observation. Okay, J is an observation, and an observation is a time-firm pair. So because you have in this likelihood these latent objects coming from these indicators, what we do is that we write down the expected log likelihood over the latent group membership. Then you get a term for the expected log likelihood. The expected log likelihood can then be maximized with an EM algorithm. When you write down the expected log likelihood, what you also get is this gamma JG term. So this is a term for each firm time observation and each group, which gives you the basically predicted probability of what IT observation will fall into which group. This is basically the econometrician's best guess for how to assign these firm time observations into different groups. Okay, so that's the algorithm. That's what we maximize. What this algorithm will spit out is a lambda for each group. It will spit out these pi terms, which are the unconditional probabilities that basically if you randomly draw an observation, it will give you the probability of what will fall to which lambda. And then you have these gamma terms. And based on the gamma terms, you can predict out a full distribution of lambda ITs. So and those are different objects that in the next few slides I'm going to go over and show you what they look like. Chris?
So even if you are, as I'm understanding, you are today only interested in the impact response, I would suspect looking at the dynamics is actually throwing away, or not looking at them, some information. If I believe kind of membership in a group, there should be some dynamic kind of information, right? That here, by just looking statically and doing the classification, I'm removing, right? So when you guys do the dynamics, you just kind of do it horizon by horizon, or?
The way we do the dynamics later is that we take the group membership from H0, and then for each group, we just estimate an impulse response function.
I see. Okay.
In principle, you could do all of this at a higher horizon, but it gets a little complicated because you have another dimension in which the errors can be correlated. We can perhaps talk about that later, but this is how we do it. We do it at 0, that gives us the group membership, and then we do group-specific impulse response functions. Okay, so before I get to the results, a few more remarks. G is a choice here, but I told you we can select that in a statistically optimal way. We use the BIC here, and this results in 4 separate groups, okay, which is it's a relatively small number of groups. We cluster by time when we compute standard errors. That's the latest prescription of the literature. As I said, we focus mostly on impact responses. I'll have some impulse response functions for higher horizons later. And then, I already said it, but let me emphasize one more time, the objects we're going to focus on is first the unconditional RIMP distribution, which means there are going to be 4 different lambdas and 4 different pi's. And then we're going to look at the predicted RIMP distribution, which based on these estimates gives us a full, basically, histogram which assigns each firm time observation to a rim. Those are the objects we're going to be looking at now.
If I understand correctly, it's kind of easy for you to fix the G ex ante. So in addition, you select the dotting like here.
Yeah.
But you could also just report all of the results by G and then see how consistent they are across the G's.
Yeah.
Just to make sure that
We could. We did that a little bit, yeah. And also, what's interesting, the BIC really, as you go from 1 to 4, you improve it, and then it kind of flattens out. We did a bit of robustness around that, but of course, if you do, I mean, if you select G, 500, it'll be a very different object.
Noisy, but just to see,
Yeah.
4 versus 6, I mean,
Yeah.
that really make a difference.
Yeah. Yeah, good point. We can easily do it, so we should probably do that. Okay, so this is the first thing. This is the unconditional rim distribution. So what you see in this table is each column corresponds to one of these groups. And then in the first block, you have the lambda estimate for each group with standard errors. And then in the bottom block, you have the pi estimate for each group with associated standard errors. So, and the way we normalize these coefficients here is that these are changes in the growth rate of basically percentage point changes in the growth rate of capital after a 1 percentage point increase in interest rates. So what do we see? If we look at the right side of this table, this is the group with the smallest responsiveness in absolute value. That gives you a half a percentage point change in the growth rate of capital for a 1 percentage point change in interest rates. But this is significantly different from 0. Okay, there's no group that has a 0 effect here. All groups have a significant response. And I should say all of them are negative. You would expect that. We normalize it here with respect to monetary policy tightening. Investment should fall. That's the case in all groups. There's a small group significantly different from 0. And then on the left, you have the large group, which has a 4 percentage point change in the growth rate of capital to a 1 percentage point change in interest rate. So that's an economically strong responsiveness. However, that group corresponds to only 5% of the firm time observations. So you have a lot of mass, essentially, in groups 2 to 4. Group 1 is the one that has a really strong responsiveness, and that corresponds to 5% of the observations. Yeah.
So employment weighted is less than 5% or less?
So this is unweighted. Yeah. I will later do some weightings. Yeah. It matters. Yeah, it matters. I'll get back to that a little bit. But this is unweighted. Yeah.
Can you repeat what the half a percentage point is with respect to what?
This is how much the growth rate of capital changes in percentage points after a 1 percentage point increase in interest rates.
What's the unconditional implication? I have a hard time in this data set to figure out what the baseline is.
Do you remember, David?
It's hard to know if 0.5 is big or small if we don't know.
I mean,
what is
so in the paper, we have a more thorough discussion of the magnitudes and compare it to the literature. But so the broad response is the big one is big in light of what the literature is. But it's yeah, indeed. But it's not kind of it's not crazy big compared to some estimates reported in the literature.
So the average homogeneous would be slightly larger than Christian Kobe and Wolf translation of the partial equilibrium to general equilibrium. It's a bit difficult to translate those. We can talk later.
Yeah.
But it's a bit difficult. But if you have like standard depreciation, you get a semi sensitivity of 1% more or less on average. Of 10% of what you're saying.
Say that again.
With a standard depreciation rate, you get roughly 10% on either. I think that Christian figure
Adrian, you had a...
Yeah, so in your intro slide, I thought, oh, this is consistent with lumpy models, and now significant even for group 4. But I guess there's a
Yeah.
question of gross versus net investment. So this is gross investment. So in some of the Lumpy models, you get a free adjustment for replacing the capital stock.
We tried,
Yeah,
we changed the left-hand side variable, and the picture didn't change drastically.
So net versus gross doesn't make a
No, no.
So then, I mean,
We-
then it's not totally clear you're holding in the Lumpy models, like at least that way. Right? 'Cause
Yeah, I mean,
it is
there
looking
is
like
no-
that
there-
small group is still moving.
Yeah, there are no non-responders. In that sense, it's very different from a lumpy model. But this large response is kind of rare. That's what this shows. Okay, let me now get to the predicted RIMP distribution. So basically what you can now do using these gamma estimates from the expected log likelihood is you can essentially convexify this table. You have the biggest and the smallest response as bounds, and then you predict out for every IT observation a histogram. And that's what it looks like. What we learn here, and I should say we also report the estimate from a homogeneous specification where we just don't allow for heterogeneity. So what you see here is a very interesting distribution where there's a lot of mass near zero, but not at zero. And then there's this very long tail towards stronger responses. All of this is a histogram over IT observations. So the next question, the general question now is, where does all this come from, this heterogeneity? So let me first distinguish between I and T. One thing we do is just a variance decomposition into within and across firm variation, and we find that 80% of the overall variation is within firms, 20% is across firms, okay? We think this is very notable because also the way people speak about it in the literature, it's always like, you know, these firms versus those firms, but it's really, it's that firm now and that firm later. At the bottom, we have a transition matrix that we can compute based on our estimate. So here, a line is a RIMP estimate.
Sorry, just to understand, so that means that all firms in some period respond a lot, and is that what?
Yes, yes. Well, not necessarily all, but any firm
it's
could.
Like, most,
yeah,
yeah. Kind of, but they all
Yeah.
move in.
Exactly.
Sorry, is this that's a transition, forget it.
Okay, so this is a transition matrix. A line is the responsiveness today. A column is the responsiveness next period. Next period here, this is not the horizon of the response. This is the impact response now and tomorrow. And what I just want to highlight here in orange, that's the transition from being a strong responder to being a strong responder again. That's a low probability. So the strong responder status is very transient, whereas the weak responder status is more persistent. So now let's go to actual firm characteristics. What we do in the paper is we basically take the laundry list of all characteristics that have been tried in different papers. We throw them in individually and jointly, and then we try a couple of new characteristics. So for all of those characteristics from the list, we have details in the paper, but let me give you some glimpses at some selected ones.
Sorry, why don't you try something about time? So it looks you're all trying something about G, but
No.
if all the variation is within firm, then why don't you put
Yes.
something like business cycle or the size of the shocks or?
So, I mean, aggregate controls are already projected out, but some of these things do vary within firm. Okay, so in particular, leverage, for example, actually the way Ottonelli-Winbury compute this is the within firm variation. That maturity, these things matter. But you're right that already from what I've told you, you know that things that only vary across firms will have a poor chance here. But we try them all.
But things like time since last adjustment, like, I mean, again,
Yeah.
I mean, I'm not sure about how much you want to push the Lumpy models, but a lot of people have been thinking about variables that predict adjustment in these
Yeah.
Lumpy models.
They are not here. We tried them. But yeah, thanks for pushing us. Maybe we want to report them in the main list. Okay, let me just show you some pictures here. So what I do now is basically for any firm time observation, I can go into CompuStat and look up the size, and I can go into our estimates and look up the predicted RIMP. And then I can do a scatter plot, or in this case, a bin scatter plot. So what we have here on the left-hand side, in the left panel, that's size, meaning as you go from left to right, you go from small to big firms. And then as you go from top to bottom, you go from weak to strong responsiveness. So what this shows is that smaller firms have a stronger responsiveness, a more negative response. That's in line with the literature. In the right panel, we do the same with age, and we find that younger firms have a stronger responsiveness in line with the literature. As you can already see, though, on the y-axis, the range of values that we're capturing there is not that big. Here are two more pictures. This is leverage and distance to default, which is from the original Ottonello-Winbury paper. And here already things are not quite the same as in their paper. So for leverage, they get a positive relationship. Ours is positive, but it's kind of in non-linear in an interesting way. And then for distance to default, they get a negative one. We get, if anything, a positive one, although kind of the range is really small. So mostly we confirm what's happening in the literature with a few exceptions. We can...
What are the -4 RIMPs in these graphs? I don't understand the thing about the y-axis.
Well, they are in one of the bins of the bin scatter. So we are being, in some sense, we're being maybe a little bit unfair here because the bin scatter doesn't allow for this, like some kinks at the end, but we go to nonlinearities as well. But they are going to be, in here, but in...
So maybe
Yeah.
the bins are not great because, again, like the previous picture, that seemed like a very good fit. But then you're telling me, again, there's someone hidden somewhere that is way off.
Let me come back to nonlinearities. Also, I need to speed up a little bit.
To do the bin scatter the opposite, like do the bin scatter on RIM and
Yeah.
then show us
Yeah.
the average of the other ones.
He's running out of time, so.
Yeah. Okay, so we can do bivariate pictures, or we can go all the way to multivariate. So here we have tables, where on the left-hand side we have the RIMP, and on the right-hand side we jointly throw in some of these characteristics. In general, again, we confirm most of the results in the literature, but we don't get a great fit in these regressions. And we do, we include nonlinearities, we include interaction terms. It's generally hard to increase this fit. Okay, should we be depressed by that finding, that there's a lot of variation that can't be explained? We think maybe not, because in general, even the unconditional investment behavior, if you put that on the left-hand side, that's also not so easy to explain. And then another exercise that we do is an aggregation exercise. So here we wait, coming back to Gianluca's earlier question. If you actually take only that RIMP variation that is explainable by observables and you aggregate that up, you get very close to the aggregate RIMP. Okay, and then we try some new things. Let me skip that because I do want to get to the model exercise. Here we have the impulse response function. I'm also going to just put that really briefly. So Chris, here we take the model 0 groups and we construct impulse response functions. And there is a lot of heterogeneity also at longer horizons. We do the predictability exercises also for longer horizons, because you might say, well, the impact response might not be explainable with size or leverage. It's about the longer horizon response, but no, also in this regression, you get a poorer fit. So let me talk a little bit about implications for structural models. We think our results give a nice new set of empirical targets for models, and what we in particular want to highlight is that the shape of the RIMP distribution is a target that should be interesting for modelers. So how do we show you that?
Sorry, before we go to the model, can I just very quickly? So, I mean, one possibility is that, so empirically this procedure doesn't work very well, and the assignment is sort of kind of random. So it would be useful to have a Monte Carlo exercise, for example, where you show that, you know what the true model is, you know what the types are, maybe the types change over time because, ages and so on, and then you show that.
Yeah, we have done that. And measurement error, with like, for example, you can assume that you have one group and you fit 5 groups and you get very little spurious heterogeneity, or you do the other way around.
Thank you. I really want to show you one more picture. So we take what we think it can be considered a canonical model of firm heterogeneity. So this is this paper from Adrien, Matt, Ludwig, and Tom in preparation for the Journal of Economic Literature, where they have one chapter on firm heterogeneity. And this is essentially a Kahn and Thomas model with a new Keynesian block. It's slightly simpler than Kahn and Thomas. So we take their model, we solve it, and we construct general equilibrium responses of investment to monetary policy. Yeah, let me actually jump at really quickly, like 20 seconds. We have 2 different calibrations of this model.
Stop watching
the game.
I was thinking we started
Okay, now I can relax. We can watch the game for 5 minutes. David,
In the Monte Carlo, it's always useful, I think, to show one case where it doesn't work.
No,
because there must be a case where it doesn't work, right?
For sure. So
to understand how extreme has to be the.
So one case, I can tell you one case it doesn't work. Is that obviously we have a parametric assumption on the errors. So if you start having
Gaussian.
yes.
I see. So you have no Gaussian errors. Okay, I see.
Yeah.
So like commutativity shocks that are, for example, fat-tailed.
Yeah, if there are Gaussian mixtures and you get 5 tails with Gaussian mixture, then maybe it can work. But yeah, we can do more on those. But thanks very much.
okay, now again more relaxed. So unlike in the Hank literature, it's a little bit more difficult to say what is a canonical model of firm heterogeneity in monetary policy. But we think this Journal of Economic Literature paper is a nice starting point. So we take this model. This is a simplified Kahn and Thomas structure with a new Keynesian block. So they're heterogeneous firms. They differ in their productivity, their capital adjustment costs, and they face a collateral constraint. We take that model and we solve it, and we study the general equilibrium responses to a monetary policy tightening. And then we compare 2 separate calibrations of this model. And basically we pick all the parameters to have the same value in both calibrations and only vary the parameter in the collateral constraint, so that captures the basically the parameter on capital. And the other one is the capital adjustment cost parameters, because these parameters are central to the investment decision, so we vary them around. So what you get from these 2 calibrations, and this you should really think of this as like a case study in a way. What you get from these 2 calibrations is first that in the left picture here, we take the 2 models and we compute the correlation between the RIMP, so the responsiveness of each firm to monetary policy, and the size of each firm. Okay, this is not exactly the same as an interaction coefficient, but it sort of goes in that direction. So these are 2 calibrations which give broadly the same relationship between firm size and the responsiveness of investment to monetary policy. However, if you construct the full distribution of these responsiveness coefficients, you get very different pictures. So I should say in the left panel, the 2 bars are the 2 models, and the black line is the data. And then in the right panel, again, the 2 colored histograms are from the 2 model calibrations, and the black one is what we get in the data. This is the picture I showed you some time ago, our distribution. So what this tells you here is that 2 different calibrations that look very similar in terms of this kind of one covariate relation with the RIMP can give very different distributions of the RIMP. And neither of them does perfectly well. So we could, you could more formally use that as a target. This is more to demonstrate that they generate very different pictures, even though on the left they have very similar features. So therefore, this is just to kind of highlight that we think this whole distribution is a target that can be useful for structural models. Okay, now I'm ending with too much time. No, okay, so just to summarize, the literature has given us a lot of interesting results, kind of covariate by covariate, and we want to pivot a little bit and argue that you should have a more comprehensive picture of the heterogeneity first, and then ex post link it to what explains that. So that's what we showed you. We showed you that there are lots of firms that in lots of time periods have a very weak responsiveness to monetary policy, but sometimes they respond strongly. And characteristics that the literature has focused on do matter, but there's a lot of heterogeneity that is difficult to explain. And that full heterogeneity picture that we get, we argue, can be useful to discipline structural models of firm heterogeneity and monetary policy. Thanks a lot. No problem. Yes, please.
If you're interested in the different mechanisms of the different characteristics that explain heterogeneity, I mean, you said the literature goes covariate by covariate. It's not exactly quite fair because most have appendices where they put the other covariates too. So
Yeah.
you can also just put all of those covariates in that regression, like interactive with the monetary policy shock,
Yeah.
and then check which one's the one that explains the most. So what do I miss if I do that, as opposed to, which is
Yeah.
much simpler, I think, as opposed to doing this more involved strategy.
Yeah, that's a fair question. The kind of, if I go to this equation here, the horse race type exercises you can do. You can just take many x's and many interaction terms. But what you cannot do is have this full distribution that also includes the latent heterogeneity. That you cannot do with that approach. And that's also the reason why we choose that to confront the models with, because we really want to highlight the value added of our approach. So I agree with you. I think, the literature has a bit underdone that, in my view, to even do the more in here. That's doable, but not all of what we do is doable with this approach. Adrian?
So one of the reasons why firms might respond a lot is something like variable debt that you have to roll over or something, and post-financial constraints. That's actually, I think, what's going on in the version of the caddy-weighted model, where you have firms that have a lot of leverage and they're at the constraints, so they're just rolling over all this from that. So that's something in principle you could kind of test directly by saying, oh, is it true that group 4 tends to be kind of firms with short-term debt or something? So
The thing is, one of the observables that we tried is debt maturity, and that's in this table as well, the third observable, and it's
not just maturity; it's kind of a combination of short maturity and a lot of debt. Yeah, something that would
Okay.
proxy like how much interest payments you have to make,
Yeah.
in ongoing.
yeah.
Like
I
just to
guess
test a bit more directly this kind of
Yeah.
hypothesis.
It's actually the interaction between the first and
yeah.
the third.
I mean, we have that. We did have that somewhere because we have a lasso where we interacted all possible pairs. It didn't quite get us there. But yeah, I think in addition to confronting the model with these distributions, we can drill down a bit more into these distributions and then link that with multiple covariate approaches, and then you can combine that. I think that's the case. By the way, here this typically like in the orange one, the constrained firms, they make up this pile on the left, and the unconstrained on the right, and in the blue they kind of coincide to the same mountain. That's how these models here are different. Yeah. Yes, Tamba.
I wanted to understand better the this sample, like stochastic volatility, but all of those are ruled out, right? So these have to be in the time domain, but sort of like firm by firm, something like, so like heterogeneous exposure to aggregate shocks or something like that has to be that 80% of the variation. Am I understanding that correctly?
Yeah, that's right.
And
It's
so
not
we have-
just
again, do we have any
time
hypothesis
variation.
Because to Luigi's point, like most of the stuff you do is in the cross section, right? So is that right? When you try to explain the heterogeneity that you find in the
Not some of it is, some of it isn't. I mean, if you look at this list, the cash ratio varies by firm and time, debt maturity varies by firm and time, default risk varies by firm and time. Size and age, they move very slowly over time, so they vary mostly by firm. But in this list, there are several things that vary within a firm.
But if there was something, I mean, imagine that the big things are all concentrated in a very specific, I don't know, in the financial crisis or something. I actually don't have the financial crisis in here, but whatever, in a specific period, in the 80s or something. But again, different firms are differentially exposed to that aggregate macro phenomenon. Would that be a potential, would that be the kind of thing that would explain the 80%?
Not really, because it's conditional on a monetary policy surprise, which should, if the surprise works well, it should be orthogonal to macroeconomic conditions as well.
No, I
You-
understand,
right?
You
But
have a small sample in the time series,
Yeah.
so it could just be a coincidence
Yeah.
in the small sample.
it could be. Yeah, okay. Thanks, everybody.
Joel?
Okay. Can you give me like?
Yeah, then.
No, there's something.
Yeah. No, but that was good.
Well, let's get started.
Okay, great. Thank you so much for putting our paper on the program. I'm very excited to present this paper on resilience versus fragility, which is joint work with Simone Treviolio, who is here just at the front, Roberto Corrao, and Giacomo Lanzani. And this will be a primarily technical and theoretical paper, but we think lots of the results are going to have pretty concrete applications. And in particular, the applications I want you to have in mind throughout is trying to understand what are the macroeconomic consequences of networked production. So you see when people talk about networks a lot, they often emphasize this view that networks make the economy fragile, by which I mean rather informally that the presence of long supply chains in production networks means that there's the possibility that small shocks anywhere in the system can have large, potentially outsized by some definition, adverse effects. However, you also see people talk a lot about how production networks could open the door to resilience. In particular, if I'm constrained to only produce locally, if the local plant that's supplying me stuff goes out of business, then I'm really in trouble. But if I have access to global supply chains and I can switch across suppliers, then it's possibly the case that that multiplicity allows the economy to weather adverse shocks and exploit the option value of positive ones. And so we want to understand when it is exactly that the production network structure of an economy could give rise to emergent properties of fragility and resilience. These will, of course, be terms that require definition, and that will be provided in due course. And then at the same time, we want to understand what are the microeconomic properties of technology that can give rise to these emergent phenomena. Okay? So what's our setting going to be for today? It's going to be what I'll describe as the canonical production network model. And if you know the paper, you don't have to know the paper, but if you know the paper, I want you to think of the setting of Acemoglu, Carvalho, Ozdeglan, Tabaz, Salehi, 2012 in Econometrica. So it'll be a static model. I know the title of the session is about dynamic equilibrium models, but this will be a static model for today. And there'll be a single factor of production, which will be labor. And then all of the goods in the economy are going to be produced by combining labor with other goods that are produced using labor. Within this setting, we're not going to innovate at all on adding new model features. What we're going to instead do is remove restrictions that are typically placed on that model. So typically people will work with models in which technology is Cobb-Douglas, like in the original Ajimoglu et al. Paper, maybe an endogenous Cobb-Douglas technology, like in Ajimoglu-Azar, maybe a nested CES structure, like in Bakai and Farhi, or other endogenous Cobb-Douglas examples, such as Kopytov et al. What we're going to do is instead we're going to say, well, let's impose only the core mathematical structure necessary to analyze these models, which is constant returns to scale in production, and let's otherwise impose nothing else on the structure of technology. And as I'll argue, this will allow for a very general and flexible theory of endogenous production networks. That's what's different about our modeling approach. What's different in terms of our focus? While much of the literature so far has focused on making statements that are local in nature, such as the seminal paper of Hulton and Bakai and Farhi, or asymptotic in nature, such as Ian Djubeka's very nice paper in Econometrica, we're going to be interested in providing theoretical results that say globally what are the properties of, say, equilibrium prices and output, that is to say, without approximation. What we're going to do today, if I have time, is talk through the following results. The first thing we'll show is we'll be providing a kind of a generic class of production network economy that is going to be sufficient to generate equilibrium outcomes in all other classes of production network economy. This will be a situation in which each sector has a menu of Leontief production technologies, which you can think of as different recipes for producing the different goods, each of which will have a different Hicks-neutral productivity, and when the sector can see its input prices, it will choose the best, i.e. cost minimizing, such Leontief technology. We'll show that this class will be general enough to generate whatever can happen in all of the aforementioned examples of economies, such as nested CES, Cobb-Douglas, endogenous Cobb-Douglas, and more. The main theoretical result of the paper will then be a primitive formula for equilibrium prices and GDP that applies in any such economy. That is, an exact solution for equilibrium prices. I'll then argue that the particular form of this formula implies various emergent properties that are relate to emergent resilience and fragility, and are relate those themselves to properties of production functions at the microeconomic level. On the way, I'll highlight exactly what restrictions we may be intentionally or inadvertently imposing when we use many standard technologies that are often used in the literature. We'll then apply this to do three additional things. In the first instance, we're going to provide a generalization of Hulton's theorem that applies in any such economy. Hulton's theorem imposes that everything is smooth so that you can differentiate everything how you like. However, in economies in which technologies can switch, those assumptions are violated. This generalization of Hulton's theorem will actually imply something of the opposite of the standard takeaway from the regular Hulton theorem, which is to say that input-output structure matters even locally. The local Domar weights are going to be insufficient to characterize propagation, even for small shocks. We'll then also provide a formula for the macroeconomic effects of changing microeconomic volatility, which will let us understand what are the effects of sectoral volatility on GDP. In that context, we'll find that standard second-order approaches necessarily provide an outsized estimate of the effect of how bad volatility is for macroeconomic outcomes. And finally, we'll provide some robust bounds on the variance of aggregate GDP that can result from microeconomic productivity fluctuations, which will allow us to provide general sufficient conditions for when microeconomic shocks can generate macroeconomic volatility. Okay. Before getting into that analysis, though, I want to show you a motivating example, which I hope will convince that for at least a number of applications in endogenous production networks, having a global approach is going to be necessary. My example is going to be a very simple one, in which there are two sectors and one choice of technology. There's an upstream sector, U, a downstream sector, D, and they're each using a primary factor, which throughout the talk will have subscript 0, and that I might describe verbally as labor, just to fix ideas. In the upstream sector, there's a Cobb-Douglas production technology with Higgs neutral productivity ZU. There's a Cobb-Douglas exponent of 1/2 on the primary factor, and it's roundabout production. So the upstream sector is using upstream goods to produce upstream output. Okay? And the Cobb-Douglas share on upstream is also 1/2. In the downstream sector, there are going to be 2 potential technologies, each of which combines in a Cobb-Douglas fashion the primary factor labor with a composite of downstream production and upstream production. This composite is itself going to be a Leontief aggregator of downstream output and upstream output. And while this might seem very special in construction, as I've already highlighted, we're always going to be able to write economies in ways that closely resemble this, albeit in general in a much more complicated way. So what's this omega representing? It's representing how much of this input you need to use in production to produce a unit of output. So when downstream sectors choosing its technology, if it chooses the low omega, it's basically saying that it will rely heavily on the upstream sector. And if it's using the high omega, it's saying it'll use less of the upstream sector and will potentially use more in-house solutions. And its question will always be, which of these choices of technology minimizes cost? On the household side, this is necessary to compute GDP. We're going to be imposing that they have Cobb-Douglas preferences over the downstream good and the upstream good. Are there any questions on the setup of the example? No? Okay. So the key question here, just to visualize these 2 networks, is which network configuration occurs. When omega is low, we're using a lot of the upstream and downstream. When omega is high, we're using a lot of the downstream and downstream production. And of course, the key thing here is which network arises is endogenous. It depends on which of the goods is cheaper, which will itself depend on which of the sectors is more productive. So we can't just take the network structure as given. It will be an equilibrium outcome. So I set up this example in a very intentionally simple way because you can solve it by hand. So if you solve the cost minimization problem of the upstream sector, what you get is that its price is equal to 1 over upstream productivity squared. If you solve the problem for downstream prices, well, you have this kind of cost function of this Leontief composite. The key feature of Leontief production functions is that they have linear cost functions. So the cost of producing this Leontief, when you have a technology weight omega, is simply the weighted average of the weights multiplied by the input prices. You're combining that then Cobb-Douglas with labor, so your ultimate price is the square root of that price of the Leontief composite. And then you have to solve this fixed point for PD. If you do that, and then you plug it into the solution of the households problem, then you can derive a formula for log real GDP, which has the following shape. Of course, the exact formula, I don't really want you to focus on. I want you to focus on a really important feature of this formula, which is that it's kinked at exactly the point where the productivities cross. This is the point at which upstream or downstream becomes more or less expensive, which is the exact point at which the choice of input intensity in the 2 sectors changes. So now we might like to ask, do state-of-the-art local methods, which we're all used to using, which would be, say, the second-order approach of Beccai-Farhi, or even higher-order polynomial approaches, capture all of the qualitative features of these economy? We show in the paper how you can have pretty large approximation errors in this kind of economy, but I'm less worried about quantitative errors as much as qualitatively things we might be ruling out through our use of solution method, because that's meaning that there are properties of the model that might be happening that could be economically interesting that we just can't see because of how we're solving it.
Sorry, clarification.
Yes?
Is the key, the kink really key here, or you could have a CS that is very close to Leontief but is smooth, and then that doesn't work?
So what does it mean by work? So you can define, of course, the Taylor approximation. It's just going to break down really fast. So if you, and we show in the paper actually, that if you have, say, a CES aggregator, if you like, of these Leontiefs, right, you could ask, well, if I want to have a sufficiently flexible CES there that is good enough to approximate the qualitative features I'm about to show you, how well does that fare quantitatively? And the answer is it's really quite poor. And it actually does much worse than even first-order approaches when you do that. And the idea is, as soon as you start putting really nonlinear functions in to approximate functions that are non-differentiable, but actually not that nonlinear, you can start doing much worse than you might otherwise think. Okay, so In particular, just show you some qualitative features, I'm going to ask, how is it that a mean preserving spread of upstream productivity affects expected GDP? So we might think of this as saying, if I have upstream volatility, how bad is this for the economy on average? So to do this in an extremely simple way, I'm just going to say that upstream productivity is either a big value with probability 1/2 or a small value with probability 1/2. What I'm plotting in the blue line is the actual effect if you compute this. What you can see is that as you initially increase volatility, that's bad for the economy on average. Intuitively, locally, you're using one Leontief technology. You have rigid input requirements. So adding volatility is really quite bad for you. However, once volatility starts increasing beyond this point, volatility starts being good for the economy on average. That's because there's in essence some aggregate option value that arises from the fact that the sectors can choose which technology they're using. And so volatility starts becoming good on average for the economy. Eventually, again, it starts becoming bad. Why does it start becoming bad? Because at the end of the day, even though you can switch, you're using one of two Leontiefs. And neither of those guys like having volatility, so things start getting bad again. What I'm plotting here in orange is what you get instead under a first-order approximation. Necessarily with first-order approximations, there's no effect of volatility on average because everything is linear. So of course you miss this. What people typically do in the literature to capture this kind of effect is a second-order approximation. Now locally, you're always on one specific Leontief technology. So things are always going to be bad if you only use the local information. So you're just going to extrapolate this initial negative part all the way down and completely miss this S-shaped response, where volatility is initially bad, then becomes good, and then becomes bad again. Yes?
Could you explain again the option value effect, please?
Yeah, so if you like, right, what's happening here is that, seen from the perspective of this, right, the first welfare theorem is true here, right? So we're kind of always going to be choosing the efficient configuration of production, right? And so when we're really bad at making downstream stuff, when it's an unproductive sector, we're going to produce downstream stuff using upstream stuff more intensively. Conversely, when we're really good at making downstream stuff, we're going to want to make the downstream sector more roundabout in its production. We're then enveloping over those two possibilities and choosing the better one each time. So it's like we're choosing between two options, and volatility, when you're choosing between different options, is normally something that you like. That's why I'm calling it option value. That makes sense? Okay, great. Okay, so what I hope I've convinced you here is, at least in a simple example, that we can miss qualitative properties of the economy if we use even state-of-the-art, not first order, but higher order local approaches. What I'm going to do in the rest of the paper is try to give a global analysis of production network economies that doesn't require the use of approximations.
How do the omega bar and lower bar change this? Is it important or not?
It would make a quantitative difference, right? Because it would change how good it is to switch. Like if they're very similar, there's basically no value in switching.
But there's nothing interesting in it.
It could be interesting, but it's not going to change the kind of qualitative feature that you can rule this thing out. Yeah, I wouldn't say it's uninteresting. That could be very interesting. Depending on the degree of flexibility you have, that will of course govern the economic magnitude of this force. Great. So what's the model going to be? And as I promised, there's going to be very little innovation on the modeling side, only in terms of making things more general. So there are n sectors indexed by I, which are producing according to a production technology F sub I. Here we're taking in the primary factor, which again I'm always denoting by subscript 0, and then a vector of intermediate inputs. The Higgs neutral productivity is going to be denoted by Zi, and I'm going to call this G tilde I the kind of production function. What are we going to assume? We're going to assume that this production function is positive homogeneous, which is to say it's constant returns to scale, non-decreasing, more inputs give you more outputs, continuous, and such that you can't avoid to use labor. So the optimal expenditure share on the primary factor is bounded away from 0. What we show in the paper is that any such economy, by redefining the sectors, can always be written exactly such that this G tilde is Cobb-Douglas in the primary factor of production and a nonlinear composite of all of the produced goods. in the economy. So in what follows, I'm always going to take G tilde of this form, as you can always write things in this way, something that we prove in the paper. The final thing that's important to note is that we're normalizing, and apologies, this G tilde, such that it's, sorry, no, I'm actually not apologizing. We're normalizing this G such that its maximum value is equal to 1 over the simplex. And when you see this triangle throughout, I mean the simplex. So the set of all n-dimensional positive vectors that sum to 1. Okay? All this means is it means I have a consistent definition of what productivity means. Okay? Any questions? This is kind of the important slide, if there are objections. There's time for objections later, but okay. Good.
The betas are, they come from, can you remind the betas?
Yeah, so this is coming from something we prove in the paper, which is that you can always represent any economy with this structure under this assumption as being like this.
So beta is some convolution of like primitive parameters?
Yes,
Okay.
exactly.
But it's all parameters?
Yes, it's all parameters, exactly. Great. So what's the classic example of such an economy? Well, one is Cobb-Douglas, right? Where we're using all of the inputs in a Cobb-Douglas fashion. I'd say this is the main production function that's used in applied research. This is also implicitly what we're assuming when we linearize general models, right? So whenever I see a general model and it's linearized, I always think at the beginning they assumed Cobb-Douglas, okay? You could also accommodate much more general things. So for example, you could imagine a world in which each sector can choose its usage of different factors through these alpha parameters, and also how flexibly it could substitute between different inputs, the elastic substitution, subject to some opportunity cost in units of productivity given by this shifter A. So this is saying, if goods are expensive, maybe you can shift to change your input mix, or you can make yourself more flexible, but that might come with some opportunity cost that if you shift your mix, you're going to be less productive. Okay? Great. What about the household side? So this won't be important, as we'll see, for characterizing equilibrium prices, which I'll be doing for most of the analysis. But just to fix ideas, when we compute equilibrium GDP, I'm going to keep things simple and impose for today's talk that we have Cobb-Douglas consumption utility. So the household's going to maximize its utility, subject to the constraint that its consumption is less than 1. This is coming on the income side because they supply inelastically a unit of labor at a wage which is normalized to 1. So their income is 1. A competitive equilibrium here will be standard. So it's going to be a profile of prices, quantities, and consumption, such that firms minimize costs, households maximize utility, firms make no profits, and all markets clear. Okay? Some preliminaries. I'm going to define the cost function of sector I as the minimum expenditure way of producing a given unit of this intermediate composite G. So this is going to be a cost function. It's a standard. What we're then going to do is define a transformation of this cost function via this log cost operator, which is defined row by row by saying that Ti of P, where little p denotes the logarithm of big P, is the logarithm of the cost function evaluated at the exponentiated log prices. In a Cobb-Douglas world, this would be nothing more than the inner product between the exponent vector and the log price vector. So this would be linear in the Cobb-Douglas world. In equilibrium, firms price at their average cost, which is their marginal cost, because of constant returns to scale. And so equilibrium prices always solve this fixed point equation. And if you rewrite xi as minus 1 of 1 minus beta log z, you can kind of read this intuitively as the firm's price is some kind of weighted average between its transformed productivity and its log cost. Okay? And this, you can see here, intuitively looks like it has a contractive structure. Indeed it does. So there's always going to be a unique solution for every x to this equation. We're going to call that pi of x, the unique equilibrium price vector. Our main results will be concerned with characterizing this and its properties. Any questions? Okay. So first, we're going to provide this endogenous Leontief representation, and then we'll move to characterizing the fixed point. So to do this, I'm first going to define an object, which is a standard object, which is the relative entropy. So given two elements of the simplex, two probability vectors, the relative entropy between W and W tilde is going to just be the sum of the w's times the log ratio of the w's to the w tildes. Given this, we can state the result. The following are equivalent. There exists a regular g, i.e. a production function satisfying all of my assumptions from before that induces t, and the t function is monotone, translation invariant, i.e. if I add a constant vector to all of the arguments, t goes up by the same number as that constant vector, normalized, so it's normalized to some baseline value, and such that if you de-x-logify it to go back to the cost function units, the resulting cost function you have is concave. Okay, so this first two is just to say that we could always work with g, or we could work with t, or we can go back and forth, so long as we do our homework, and we make sure that when we write down a t, it has all of these properties. Moreover, if you give me your favorite g, we can always represent the induced t via the following formula. That is to say, the induced log cost function is a min-max over vectors of weights of an inner product of the weights and the log prices minus the relative entropy between the weights under the maximum and the weights under the minimum plus the logarithm of 1 over the original production technology evaluated at the weights in the minimum. Okay, so this was a mouthful, okay? But what's happening here? This might not seem even helpful. This might seem like we've made our lives worse, okay? So what's going on here? The key thing I want to emphasize is that this shows that any t, any log cost function, can always be written as a min-max of an affine function of log prices. So we'll note here, right, this additive term, right, in this curly brackets, doesn't depend on p. So this is an affine function of p, and that's going to be a really key property for later on. But how do we get here? So the first thing we show is that you can write any cost function in the following way. It is itself the minimum over vectors of input weights of the sum of those weights and the input prices divided by your production at those weights. This is itself the cost function that is exactly what you would obtain if you had this kind of production function, which is to say, in this inside, you have a Leontief production technology with some input weights W tilde and some productivity at those weights GW tilde, and then you always chose the resulting Leontief technology that led to the greatest amount of output. So you're always choosing between this menu of Leontief technologies with heterogeneous productivities. Okay? You can kind of see intuitively that it's like choosing the best Leontief is like choosing the cheapest one. Okay? What we then show is that if you take the logarithm of the cost function of a Leontief technology, so take a log here, right? You're going to get a log of this guy, which is just a log of the inner product between W tilde and e to the log prices, plus log 1 over the guy in the denominator, right? What we then notice is that this guy here is itself the value function of another optimization problem, which is maximizing, given a new vector of weights, not this log sum x character, but simply the inner product of the new weights and the log prices minus the relative entropy. And this is a well-known expression. This is what's called the Donska-Varadhan formula, and it comes up a lot in economics in discrete choice. Okay? And you might have seen this before, right? Like maximizing expected utility with an entropy cost is like having logit choice, right? That's exactly what the result that underlies this. Okay? So now we've seen how we get to this t, and we've seen how we can interpret it as arising from the fact that all of these economies are equivalent to endogenous Leontief economies. What we now want to do is to use this to characterize equilibrium prices. So to do this, I'm going to do a couple more definitions. So what I'm going to define is calligraphic W is the set of all row stochastic matrices, i.e. matrices whose rows are positive vectors that sum to 1. This is just the set of all possible input-output matrices that we could possibly think of. Given any input-output matrix, we're going to define the Leontief inverse, omega of W, as 1 minus beta times the identity matrix minus beta times the input-output matrix to the power of minus 1. Right? This is just the regular old Leontief inverse that we're used to seeing. And the standard result, say of Acemoglu et al. And other people, is that under fixed Cobb-Douglas technology, the equilibrium log prices are simply the Leontief inverse applied to the log productivity vector. Okay, yeah.
So was beta the primary factor share of one sector or all sectors?
Good. So, as written, of one sector, but the argument I made, that I asked you to trust me on, because I didn't show you the steps behind it, is that any economy of our more general form can be rewritten by redefining the sectors such that it's as if they all had the same primary factor share. Yeah? So this is just going to make things particularly simple for X. But you could start from this, but we're going to use this rewriting of the economy to get a particularly simple expression. Yeah.
I'm wondering if there's a short answer to this. If they have like a simple, imagine, is there some simple production function, just like Cobb-Douglas production function, where you can say something about what this Leontief, like it seems like you're saying there's a Leontief version of everything.
Yeah.
Is there some way to say what the Leontief version of the Cobb-Douglas looks like?
Yeah, absolutely. So in the Leontief version, you see it explicitly here. So the G star is the Leontiefication. The G is the original Cobb-Douglas. So it's like saying that your G is the Cobb-Douglas of those weights. More evocatively, you could write that in a different way. You could write the G as E to the minus of the relative entropy between the new weights that you're choosing and the fixed Cobb-Douglas weights. So it's like saying that you have an opportunity cost of changing your input mix that is related to how distant your new mix is from your baseline Cobb-Douglas mix, where distance is measured by the relative entropy function. Great. And of course, for any production function, you go through a similar exercise. In fact, CES, for example, is not related to relative entropy, but it's related to Rényi entropy. And in particular, the CES parameter governs the Rényi entropy parameter. And you can go through other production technologies and think about what notions of statistical distance they correspond to in terms of the opportunity cost. Okay, great. So we want to solve our general fixed point equation, right? So just to recall, we have sector by sector that its log cost function t is given by this. So now we can plug this into the fixed point system from earlier, just where the t was, right? And all I'm doing here, with some abusive notation here, is stacking those fixed points into a vector. Okay? So what this says is that the price is the weighted average between the productivity, beta times t, and we just learned that we can always write t as a min-max of an affine function of the log prices with this affine disturbance. Okay? So a naive idea that you could have, which would be very nice, is you could forget about this min-max naively, just like pretend like the min-max isn't there, right? Then this is just a linear system in P, so you could just invert it, just how you normally would for solving a Cobb-Douglas system, and you could solve for P. And if you did that, you'd have that P is the Leontief inverse applied to a distorted vector of productivities, where the productivity distortion is this production wedge, which is essentially saying how much less productive are all of these sectors because they've moved their technology away from some most efficient baseline. So it's kind of capturing the adjustment costs that are implicit in general technology. So that would be naive. What the general theorem shows is that that isn't so naive. In particular, if you ignore the min-max, compute the fixed point, and then apply the min-max, you get exactly the same answer as if you computed the min-max and found the fixed point, which is to say that you can commute the operations of taking the min-max and finding the fixed point and do them in the wrong order, so to speak. So if you do them in the wrong order, what the theorem is claiming is that you'll get the right answer. So what's the statement? For any productivity vector, the unique equilibrium log prices are given by the following formula. Prices are a min-max of this formula that obtained in those, if you like, distorted Cobb-Douglas economies, where the min and the max are over pairs of input-output matrices. Okay? In the sequel, I'm going to be interpreting this minimum and this maximum as representing resilience and fragility. Now, you can use this for other things. In particular, if you wanted to compute log aggregate GDP or welfare in this economy, that would just be in log units, the inner product of the household's expenditure shares and the log prices. Because in this min-max representation, notice what I'm saying, right, is that this is n-dimensional, right? So what this is saying is that there is a pair of input-output matrices that simultaneously min-maximizes this vector in every entry. Because you're simultaneously solving all of these saddle point problems, what you can do is you can just pass through this Xi inside the min-max, and then you have a formula for equilibrium GDP. Okay, any questions here? Okay, so what I said is you can just do the naive thing, and it gives you the right answer. And so this is kind of the main result of the paper, and now we're going to apply it to try and say a bunch of things. This I already said verbally. So the first application, resilience and fragility, how I started the talk. So we might think of defining resilience, and this will be our approach, as saying at the sector level that you have a concave log cost function. Why do we like that definition? It says that as a producer, if I had a mean preserving spread in my input prices, would I like that or dislike that on average? Okay? So it's like saying if I have a concave T, that I'm a sector that substitutes well across inputs, so I kind of benefit from variance, right? Think of like perfect substitutes, right? I really like it if my input prices are more volatile, because I'm always going to choose the best thing. On the other hand, we have fragility with a convex log cost function. So there we have a mean preserving spread in input prices raises my costs. So because I have rigid input requirements, I'm going to be hurt by variance, like with the Leontief technology. How do these concepts map to what we're more familiar with? Well, if I assume that the production technology of a sector I were CES, with elasticity of substitution sigma I, it would be resilient if and only if sigma were bigger than 1, and it would be fragile if and only if sigma smaller than 1. So in the CES setting we're familiar with, these notions map to what we might be familiar with. Beyond that, they provide a specific generalization. Yeah?
Tell me if this makes sense. So in the example at the beginning, which was very useful, I thought, is initially you had fragility and then you had resilience. Is that the way to think about it?
Yes, essentially. And so by this global definition, the economy I started with will neither be resilient nor fragile. Whether or not it likes variance will depend on how big the variance is. So it's going to be in neither of these two cases, and that will be the general case. So in particular, I'll say the economy is resilient, respectively fragile, if equilibrium prices are concave or convex in shocks. So we can first characterize the property of resilience in terms of technology. So we can say exactly which production technologies are those that induce resilience of the log cost function. In particular, a sector I is resilient, i.e. has a concave log cost function, if and only if it is generated by a production function that is endogenous Cobb-Douglas, which is to say, there exists a non-empty convex set of technologies, which in the convex case can be thought of as just Cobb-Douglas exponents, and a production shifter, which is saying how productive am I at operating these different Cobb-Douglas technologies, and then I'm always just choosing the one that gives me the most production. Okay? And in particular, this production shifter is necessarily log concave. So what this does is it gives you, if you like, a characterization of this very popular and applied work, endogenous Cobb-Douglas technology. And so what this is saying is both bad news and good news if you like this technology. The bad news is that you're hard-coding resilience. Any technology like this is always resilient. But the good news is, which I think is quite nice, is that insofar as your goal were to capture resilient technology, what might seem like a restriction is actually not a restriction at all. It's completely general. Moreover, towards interpreting the general formula, if every sector is resilient, then that is preserved at the aggregate level, i.e. the economy is resilient, and moreover, the formula for equilibrium prices can be reduced to saying that it's the minimum of the Leontief inverse of a modified productivity vector, where that production wedge from earlier reduces to the as-if productivity opportunity cost of operating different endogenous Cobb-Douglas technologies. What I want to emphasize here is that we just have the minimum. So in these resilient economies, we just have the min, versus the general min-max structure. And so I'll be interpreting the minimum generally as arising from resilience. Conversely, we can think about the fragile case. So I'm going to say that a function f on a subset of the simplex is entropy log convex if the logarithm of that function plus the entropy function is itself a convex function. So you should think that this is just like a really convex function, right? Because if I have a function and I take its logarithm, I'm making it more concave. The entropy is a concave function, so I'm adding now, making it more concave, and adding a concave function to it. If after I do all of that, you stay convex, I'm going to call you entropy log convex. So it's like you're really convex. With this, we have the following characterization. A sector is fragile if and only if it is generated by a production technology of the following anti-Cobb-Douglas form. You can think of this as a kind of task-based production technology where I have this set of tasks, I'm using all of my inputs to produce these tasks, but at the end of the day, I'm just like rate limited by the task of which I produce the least. Okay? So that's a characterization of fragility. Moreover, if we're in a world in which every sector is fragile, then, once again, fragility is preserved at the macroeconomic level, and moreover, we have just the maximum in the general representation for prices, so we lose the minimum. Okay, so once again, what I want to emphasize from this application is that the general formula is encoding the fact that equilibrium prices are neither concave nor convex. They're being shaped by resilience coming from input substitution and fragility coming from rigid input requirements. And how I've justified that to you is by saying, well, if I look at resilient and fragile economies, then I respectively turn on and off the minimum and the maximum in the general representation.
John?
Yes?
Those definitions of fragility and resilient are not unique. No, I mean,
Absolutely.
You define fragility. You could think of a network being fragile because there's a sector which is very central and has high volatility, for example.
Yes. Yes, this is...
So, could you think about that definition?
Yeah, so here there's no real notion of centrality globally because the network is endogenous, but you could think about nonlinear centrality measures. In fact, Roberto, Simone, and Giacomo have some very nice papers thinking exactly about nonlinear centrality measures in networks. What I will do just now is relate it to one concept that is particularly familiar that you might think of as a natural definition of resilience and fragility, which is elasticity of technology. So I'm going to say that a sector is elastic if its log cost function is supermodular, and inelastic if it's submodular. Why am I using this kind of unusual definition of elasticity? Because if we were to be in a situation where the log cost function is twice continuously differentiable, then if we defined the pairwise Alan-Uzawa elasticities of substitution, then we'd be able to see that they're equal to 1 plus the cross-partial derivative of t in the prices for inputs j and k, divided by the product of the partial derivatives. Now, these t's are monotone, right? Higher input price, higher costs, right? So these numbers in the denominator are strictly positive numbers. So whether or not the Alan-Uzawa elasticity is bigger than 1 or smaller than 1 is 1 to 1, with whether or not, at least locally, you have a supermodular log cost function or a submodular log cost function, right? Because that determines whether or not the cross-partial derivative is positive or negative. So now to your question, Gianluca, we can exactly relate these two concepts. In particular, if a sector is elastic, then it is resilient. So this is, if you like, overkill for ensuring resilience. And they only coincide with each other, in general, if you have exactly two inputs. So with exactly two inputs, our notion maps to the standard notion. With more than two inputs, they're different. But an elasticity would imply our concept. Now, why do I want to think about our concept as maybe being the more natural one, although at the end of the day, this is kind of aesthetics? Because elasticity, defined this way, really reveals that it's about how much you like or dislike correlation, right? If you have a supermodular function, right, and here a big value is bad, it's like saying if your input prices are more correlated, your costs are going to go up on average, right? Whereas resilience, as we've defined it, is about risk. It's like saying if I spread out your input prices, when is that going to be good or bad on average? Okay? And so what I think I've tried to illustrate via the general structure of the fixed point relating to the trade-off between the minimum and the maximum, which themselves respectively correspond to my definition of resilience and fragility, is that the general trade-offs of these economies relate to how they handle risk rather than correlation. And while they're related, outside of the two-input case, the elasticity or correlation notion is slightly overkill. In the paper, we also talk about another notion of resilience and fragility, which I think relates a little bit more strongly to your intuition, which is, as an economy, as I make a negative shock bigger, does its like unit effect get worse? Right? So what's the sense in which big shocks are proportionally worse than small shocks? That is itself going to be a weaker notion than our notion of resilience and fragility, because it corresponds to concavity and convexity around 0. But I'll talk more offline if that's of interest. And of course, these are just words, and so there are many other things that people might have in mind, and I'm just providing one potential formalization of these concepts that I think has nice relationships to the property of the model. Okay. As the next application, I want to show you a generalization of Halton's theorem, which I think, at least in the economies we're studying, implies that the standard conclusion of Halton's theorem has maybe taken a little bit too seriously. So to do this, I'm going to think about how small shocks affect the economy. So we're going to fix, like in Ian's Econometrica paper, a direction of shocks d, and we're going to scale their size by t. And I'm going to define the average effect of a shock to productivity in direction d of size t as just the kind of the difference divided by how big the shock is. And then to ask how small shocks propagate, we're going to take the t positive to 0 limit of this character. Okay? Now, we know that the log cost of each sector is given by this. We showed that earlier. So we're going to define now the set of input-output technologies, input-output optimal technologies, i.e., at prices p, what is the set of I/O networks such that the choice of weights in the endogenous Leontief representation is optimal for each sector? Given such a W tilde, we're then going to define, if you like, the expenditure share function by this Lij operator, which is saying that if you have a Leontief technology W tilde and the prices are given by p, how much is each sector going to spend in share terms on all of the other sectors? With this, we have that the effect of small shocks is well defined and always given by a minimum over all of the production networks that potentially support the equilibrium at the given unique equilibrium prices of the Leontief inverse, given the expenditure shares induced by that technology applied to the direction of shocks that we're considering. So for every direction of shocks, it's always well defined to ask, what is the effect of a small shock? But the direction that governs shock propagation is not independent of the direction of the shock. Intuitively, like in my earlier example, if you're approaching stuff from upstream being more productive or downstream more productive, in one situation where upstream is more productive, we're using the Leontief technology that uses more intensively upstream. When we're approaching that from the situation in which downstream is more productive, we're using downstream more intensively. Now, even as I pass to the limit, I'm still using just one of those technologies. So depending on which direction I move, I'm going to be enveloping over those technologies, and that's what's happening here with the minimum. And you can think of this as like a kind of analog of the first welfare theorem, which is saying that among all of the cost-minimizing technologies that prevail at equilibrium prices, if I perturb productivity, prices are always going to go in the price-minimizing direction. Now we can apply this result to derive a generalization of Halton's theorem. So I'm now going to define the effect of a small shock on equilibrium log GDP as upsilon 0. I'm going to define E of x as the set of competitive equilibria that prevail at a given vector of log productivities. And for every possible equilibrium in this set, we're going to define the Domar weight vector as the vector of sales shares of nominal GDP. Because of my normalization of the wage to 1, nominal GDP is 1, so this is the Domar weight vector. There's no need for the denominator there. With this, we have the following. Upsilon is directionally differentiable, and moreover, the derivative of GDP in small shocks is the maximum over the vectors of Domar weights that support the equilibrium at x when we're moving productivity in direction dz. This is saying that different directions of shocks will propagate in different ways. So there's no one set of Domar weights that is sufficient to govern shock propagation. Intuitively, if I'm at an equilibrium and I have an observed set of Domar weights, say in the BA input-output data, and then I would have a shock that would induce technology switching, those Domar weights are going to be stale. They're not going to govern how the shocks propagate, and what's happening is we're always going to be choosing the most advantageous Domar weights that arise in aggregate. And so this, I think, conveys the opposite intuition of Halton's theorem. Domar weights are insufficient, even locally. Okay. In the final thing, I think I have one, do I have 1 minute? 1 minute. I'll just quickly show you, as a final application, how you can use our results to compute the equilibrium effect of increasing microeconomic volatility. So if you define average log GDP given a profile of microeconomic productivity volatilities as y of s, and if I define d of lambda as the set of x such that equilibrium is unique, not equilibrium prices, but equilibrium is unique, and if I define this Domar weight function as mapping those to the corresponding Domar weights, then we have a formula for the equilibrium effect of increasing microeconomic volatility. It has two terms, the first of which is kind of an exact version of the Bucay-Farhi logic, which says that when I increase volatility, what I have to look at is the average smooth changes in Domar weights. This is an exact version of Bucay-Farhi. But there's a second term which arises from this singular measure, which is coming from the fact that Domar weights can jump. Even though those Domar weights are zero measure in the space of shocks, they're of equal magnitude to the smooth changes, because even though they're infinitely rarer, they're locally infinitely more important, and so they become of a comparable magnitude. Okay? If you have a smooth technology, this result gives you an exact justification of the Bucay-Farhi logic. If, for example, you have a popular specification, which is a finite number of Cobb-Douglas technologies over which you envelope, the Bucay-Farhi term is exactly zero, and the entire contribution comes from the singular piece. And so you completely miss this using standard approaches. In the paper, we also provide some bounds on the volatility of Domar weights. I'll skip that in the interest of time, and conclude by saying we provided a general analysis of the properties of production networks, and I've tried to argue that what we've learned from this analysis is that the standard methods that we use have the potential to obscure qualitative properties, and that I hope that by using some of our methods, we can achieve a richer understanding of the properties of production network economies, and if production networks, and when, make the economy resilient and or fragile. Thank you so much.
So this year we are doing something slightly different, which is we are going to have yet one more paper at 5 o'clock. It's going to be a very nice paper because I have looked at it. So stick around. BRs is all you need.
A signal work.
One more minute.
have shown over the last 2 days that to play football properly, you need to speak Spanish. Now we are going to show that to run beers properly, you also need to speak Spanish. We have absolute advantage in everything.
Okay, so thank you very much to the organizers for including the paper in the program, and thank you to everyone that is here and is not watching the game. My co-author is Juan Rubio Ramirez. He is not here. He is in Spain watching the game. So I'm kind of alone presenting this stuff. And I hope this is going to be a fun paper to end today's sessions. I don't know how many of you have heard already about the transformer model, but I would be willing to bet that even today, everyone in this room has used the transformer model and even probably paid for it, because this is the T in ChatGPT. And you know, whatever is your favorite AI LLM, whether it's Claude, Gemini, the underlying statistical model that is behind it is based on this paper here, Vashwani et al., published in 2017 by Google researchers. This paper basically has 260,000 citations and triggered the revolution that we are living today in terms of AI. And as you probably know, what this model is doing is basically trying to come up with a probability distribution over a sequence of text. And you start thinking about this, and you may think, and that's what we thought, that, hey, maybe there is a natural application of something else that is a sequence, which is time series data. But of course, it's not obvious at all that a model that has been developed for language is a good idea to apply to time series, and in particular macroeconomic time series, where we don't have the millions and millions of observations that these models are usually trained with. So the promise, you know, if this whole enterprise works, is that we could come up with something that represents a general, flexible, and scalable framework to model multivariate data, and particularly useful if we have unknown, a priori unknown forms of nonlinearity and state dependence. And here's kind of our want operator. For today, we would like to have, and the machine learning literature has not provided us, a formal econometric framework for interpreting this class of models, and especially conducting inference in the time series domain, and in particular in the small sample domain. We would like to think about appropriate priors for economic time series, and we would like to investigate the performance with real-world data and data sets common in economics and finance, and this type of sample sizes that we typically have. Okay, so what we're going to do in this paper is formalize the connection between the attention mechanism and classic time series models that probably everyone in the room has heard about. And we are going to arrive to this possibly surprising result that this model that has revolutionized the world and has raised, you know, hundreds of billions just this year is just a VAR. Okay? So I'm being a little bit humorous, but we're going to show that the attention model can be recast as a time-varying VAR, in which the time variation is a parameterized function of the data, as well as a set of dimension reductions that are closely connected to those imposed by dynamic factor models and by extension dynamic stochastic general equilibrium models. And we're going to call this kind of adapted framework attention-based vector autoregressions, or attention VARs. We're going to develop Bayesian algorithms for inference that are not going to require any filtering of latent parameters, and that's why we are going to think about this as kind of observation-driven rather than parameter-driven. And we're going to propose shrinkage priors centered around the familiar time invariant structures that are going to be special cases of this framework. And we're going to extend to the conditional covariance, like 90%, as far as we can tell, of the work in machine learning has been about the conditional mean. We will look at the conditional covariance as well, and we're going to illustrate this framework with several applications. Today I'm going to speak mostly about the theory, but at the very end I will show you a little bit of real-world stuff as well. Okay? So, in terms of literature, we see this paper as trying to bridge across two highly disjoint traditions that are separated by, I would call, I mean, I'm sorry for any computer scientists in the room, but an insurmountable wall of jargon that is not very accessible, and that we're going to try to kind of demolish and translate things into the econometric terminology. And we're going to see that this is actually much more connected to models that economists have been using for many decades than what is immediately apparent. and in particular, time-varying VARs and reduced rank VARs and factor models. In the machine learning literature, these models, transformer models and attention models, are already being applied to time series applications, in particular forecasting. However, what we see our contribution relative to the work that is being there is to provide theoretical foundations and, again, develop appropriate priors and demonstrate that small sample inference is feasible and there is good performance for this class of models. Okay? All right, so the presentation is very straightforward. I'm going to talk a little bit about the theory of these models. I will then go into the economic interpretation and kind of bringing it back to concepts that are very familiar for us. I will talk about the priors and estimation algorithms, and then I will finish with just a little bit of application. Okay, so we're going to be working in this framework in which we have our object of interest is an n-dimensional vector of time series. And what we are interested in modeling are the first two conditional moments. And these moments are going to be a function of some past observations. And that applies for the conditional mean, and it applies for the conditional variance. Now, I am going to spend 90% of the time today on the conditional mean. In the paper, we develop further the conditional variance. So here's the first instance of kind of jargon translation. What in this literature is called the context window is basically the observations that we are going to use in order to form the conditional mean. You know, if you're thinking of ChatGPT, your prompt, the stuff that you are typing and pressing send, is this context, and everything that you have written before, for us, is going to be a few lags of the data that we are going to use in order to calculate our expectation of the next observation. And the context length, you know, depending on how addicted you are to using Claude and all of these models, you may have heard of this, is just going to be the number of lags in the window. And theta is just going to collect the parameters. Let's go to our basic textbook VAR model. Here, the conditional mean is going to be an affine function of the context window. It's going to depend on some lags, and we're going to have these matrices AL, and we're going to have P of those. And that's sufficient to compute this mean, and in the case of the conditional variance, it's just a parameter. Okay? All right, so let me take a few minutes to explain the attention mechanism, and then after giving you the machine learning style explanation, I'm going to translate it back to the econometrics. So we start with our observations. These are the L lags that we are going to use to compute our conditional mean. And then we're going to transform this into something that is usually called embeddings. If you look at the formula there, you will see that the embeddings are nothing more than an affine transformation of the original data. And there is going to be one embedding per each of these lags. So this goes from L equals 1 to capital L. And you're going to see that there is a term, PL, which we're going to call positional, in this literature it's called positional encoding. And that's basically going to identify which lag are we referring to. We're going to take these embeddings. Oh, I forgot to say something that is quite important, which is that the dimension of the embeddings is going to be D, which is going to be potentially lower than N, the number of variables. So we are mapping the original data into a potentially smaller dimension, and I will be very clear later about what is the interpretation of this. Yes?
Just to be concrete about it, do you want us to think of N as a super high dimensional object now?
It could be whatever you want. It could be 4 variables, you know, your favorite macro variable, macro VAR with 7 variables. It could be 150. The only thing that matters here is that D is going to be equal or smaller than N. Now, one little footnote. I have highlighted the embedding equation in blue because this is a bit of a departure from what you would find in a language model. In a language model, the original data are not numbers or time series, they are words, okay? So there you need to actually have a nonlinear mapping between the original tokens or words and the final embeddings. Here, our data is already numbers, or are already numbers, and therefore we can have a linear embedding function. And this is kind of the difference. Every time there is a difference, I will highlight it and comment on it. Okay? So we're going to take these embeddings, and we're going to do 3 additional transformations. And these are called queries, keys, and values. And the queries are going to be referring to the most recent lag. The keys and the values will be 1 per lag, okay? Hold on to this for a second, because what we're going to do is we're going to calculate something that is called the score that is going to multiply the queries with the keys, okay? Again, we have added a little term there, BL, which we're going to call a score bias. You will see later on that this is something that we think in a time series context is a good idea to add, even though it is not very common in language applications.
So one difference between the language model and time series is in the language model embedding is bidirectional. There is no like past and future. They just grab all the words before a particular word and all the words after the particular word to get rotation rate.
Yeah.
So here is like it's only from direction is only one direction.
True. Yes. Okay. So we're going to take this course, and we are going to apply this so-called softmax transformation, which is effectively the multinomial logit transformation, that is going to map this original scores into a series of weights that are greater than 0 and sum up to 1. Okay? We have this course, and now we're going to take the third of our projections, and we're going to do a weighted average using these weights that go between 0 and 1. We're going to have a weighted average of our values, which, if you remember, they are here, is the final transformation of each of the lags. And this is what is called a head, and one more affine transformation, and this is finally the expression for the conditional mean. Okay? So this is the attention mechanism as described in these papers. I should say that the full transformer architecture takes these basic building blocks and then puts it into neural networks in various ways. We're just going to work with this basic structure, and we will leave the nonlinear, the additional nonlinearities that are coming from composing this over multiple neural networks to some future work. But this is the basic mechanism exactly as it is for language models, except for the two things that I have highlighted. Okay? Okay, so before we go into the first result, one thing that I should say is that, from the point of view that you could, we have an identification issue. This is not like an identification in the sense of structural VARs. This is simply the fact that we could choose several of these matrices, these weight matrices, by the way, all of which are going to be parameters that we are going to have to estimate. But there are multiple of these weights that could give exactly the same conditional mean. And you can see very clearly that, you could just choose invertible matrices G, S, and C, and a scalar little c, and then you easily see that the conditional mean is unaffected. So in machine learning applications, this is maybe less of a concern because you are trying to maximize the likelihood or minimize some sort of loss. So you're not that concerned that you have maybe multiple modes. Here, later on, we're going to do Monte Carlo Markov chain methods, so we would like to fix this type of indeterminacies. So what we have in the paper is a set of minimal assumptions that guarantee that we have basically ruling out these invariances. If you look at these things, you will see, and there will be a more formal connection later on, they look quite similar to the kind of rotational invariances that appear in factor models. And indeed, there is going to be a very straightforward connection between these things. Okay, so our first result, which basically follows immediately from the definition of the model, just plugging in stuff and substituting, is that you rearrange things, you put the embeddings, and what you will see is that the conditional mean is going to take this form, which is an intercept that varies over time, and then a series of matrices that vary over time, multiplying the lags. So what is this? This is a time-varying VAR. Okay? It's a time-varying VAR model with some specific restrictions. Okay? So it's not any time-varying VAR model. So in this particular case, what we call single-head attention, it's going to have the restriction that each of the lagged coefficient matrices are going to be proportional to a single time-invariant matrix B, which is the product of these two W matrices. And because the attention weights sum up to 1, the sum of the lag coefficients is going to sum up to this B. So one interpretation of this B is that there is a constant long-run impact coefficient matrix. Okay? Just a little example to show what this is doing. So, minimal case, we have one variable. I choose this embedding dimension to be equal to 1. 2 lags, I just put some parameters, var phi, or phi is basically going to be this B long-run matrix, and you run through the operations, and you see very quickly that we get an AR2 in which you have these 2 AR coefficients that are moving around with these weights. The weights themselves depend on the data, so this in fact looks very much like a smooth transition autoregressive model, in which we have, the values that you have in the data are effectively giving or redistributing weights among the coefficients. And you can also see very quickly that there is these restrictions that become important, which is that the coefficients are going to sum up to this var phi. Okay? Now, one thing that is also interesting about these models is that the time variation is coming only from these alphas, the attention weights. So you could think of expanding these attention scores. You could think, what is the necessary condition, necessary and sufficient, in fact, for time variation in the model to be completely shut down and go back to a time invariant VAR model. And this F matrix, which is basically the product of the key and query matrices, whenever that matrix happens to be 0, we go back to a time invariant VAR. Okay, so this is a special case. And the conditional mean is a constant VAR like we had before. So far, what do we have? We have the attention model is effectively defining a class of time-varying VAR models. And in fact, as you have probably seen already, this is a highly restricted class, because some of these proportionality restrictions are, not something that necessarily makes sense from an economic point of view. What are these restrictions? Effectively, the matrices all have to be proportional, and the weights are all positive, so it's kind of redistributing things across the lags. Moreover, the long-run matrix B is actually going to be of rank D. This is the embedding dimension that I mentioned before, and therefore each of the autoregressive coefficient matrix is going to be of a low rank. In the time invariant case, it's also we have the situation that the sum of the coefficients is time invariant. Just to give you an idea of how restrictive this is, which is very restrictive, we have here just like a minimal little example. So it's an AR2, and I have chosen the AR2 coefficients in a way to generate, a nice hump-shaped function. We all like propagation in our models, so this is kind of the thing that we want. And it's fairly trivial to see that because the weights have to be between 0 and 1, it is impossible for this model to actually recover something like this. Okay. So this is, precisely what motivated in the original attention paper to go from what they call single head attention to multi-head attention. What is multi-head attention? Here's like another of these engineering style graphs. But multi-head attention is nothing more than starting from the same embeddings, the same observations and the same embeddings, take the operation that I just described, and then repeat it H times, where H are these so-called heads. So we will have each of these attention operations will be one head, and then we will have multiple heads. You take them all, you combine them linearly at the end, and this is your new conditional mean. Okay, so it's just a repetition of what we've done before. Same result, it follows very easily that the multi-head attention model can also be represented as a time-varying VAR. Now there are more matrices floating around, but effectively we have the same situation, and we still have the same restrictions that we have before. So the rank of each of these A lag coefficient matrix is going to be D. The sum of them is going to sum up to the sum of the B matrices across heads. And actually there is another restriction that maybe is not obvious from the slide, but if you take all of the lag coefficient matrix and you stack them together, the rank of that stacked coefficient matrix is going to be actually also lower. It's going to be the minimum of the number of heads and D. Okay. Sorry, the number of heads and L, the number of lags that you have in the context window. Once again, there is a special point in this structure, which is we set this F matrix that I mentioned before for each and every one of these heads. If we happen to set that at 0, all time variation is shut down, and then we have a time invariant VAR. Now, the interesting case is that with a multi-head attention, we can actually recover and we can represent with this model any time invariant VAR that we might want. If we have sufficient amount of heads and we make the dimension of embeddings equal to the number of variables, we can always find coefficients for these W matrices that give us back our favorite time invariant VAR. Okay? Good. So this is just a workout example. Before we could not represent it. Now we have the flexibility of having 2 of these heads. So the theorem would tell us that we need, because we have 2 lags, we have L equals 2, so we need 2 heads, and therefore we can just easily find coefficients that recover this particular structure. Any questions so far? Yeah.
So the scores are computed every time t, or all the other W and D matrices are computed once and for all?
Correct. So the W matrices are parameter matrices that depend on the entire sample, and the scores are going to be functions of those matrices as well as the observations, the Ys. Okay, so this is the model, and so far what I have shown is that this model, a sufficiently large attention model, can encompass an arbitrary VAR if you make these dimensions sufficiently large. Okay, interesting maybe, but what does do all of these things mean? What are these dimensions, in particular D, and these heads, what do they mean for economics? As I said, as long as these 2 dimensions are high enough or large enough, we can get whatever VAR we want. But what is interesting is that if these dimensions are smaller than those conditions, we do get a restricted class, but it happens to be one with a very natural economic interpretation. And to show this, I'm going to ask you to consider a dynamic factor model, but a special case of a dynamic factor model in which you're going to have R factors, but you're also going to have R variables that are measured without errors. So I'm effectively eliminating the ARMA structure of a full dynamic factor model, and this trick allows me to get actually an exact VAR representation. There's going to be this matrix S, which basically allows us to map, as you see here, from the variables I can recover the factors exactly, precisely because of this assumption that I have made. I can plug back the coefficients, and then I am going to get a VAR that has, so far, not all, but some of the restrictions that are exactly the same restrictions that we have in the attention model. Okay? Now, this is a graph that I personally find very useful after looking at all of these things for several months. So I'm going to try to explain what are these rank restrictions and what role are they playing. On the top left corner, what you have is the lagged coefficient matrix of an unrestricted VAR. And this is going to have a matrix. The blue stuff are free parameters that we need to estimate. It's going to be n squared times the number of lags. Okay, so I've stacked the lag matrices, vectorized them and stacked them, and therefore I have n squared times L. Here you have a familiar factor model. The factor model, what we have is a factorization of the dynamics of the system into 2 matrices. There is the loading matrix. We're going to have R factors and n variables, so the loading matrix is going to be n times R. And then we have the dynamic coefficients of the factors. So now this matrix is going to be R, number of factors, squared times L, the number of lags. You can already see visually that the factor model is producing dimension reduction by effectively saying that there are R factors that are driving the dynamics of the system instead of the general n variables that you would have in the full VAR. Now, what is the attention model doing? The attention model doing is basically taking the lagged coefficient matrix of the factors and is doing a further factorization and a further dimension reduction in which you are going to have the product of these 2 matrices, the first of which depends, the columns is the dimension of the number of heads, and the second one is going to be these attention weight matrices, and is here in orange, because this is going to be the only part of the model that is time varying. Okay? So what do we have here? We have a way to generate time variation in the coefficients of the VAR that is doing dimension reduction in a way that is very reminiscent of what we have in factor models, but it's also saying that the lag dynamics of the factors are effectively following a few, we can call these basis matrices, and in particular allows this reduced rank decomposition. So it's a very parsimonious way of modeling time variation in the dynamics of the entire system. And now we can do the mapping between the factor model with R observed factors that I mentioned before and the attention model. So the dimension of the embeddings is going to correspond exactly to the number of factors. The matrix WM, which was the last matrix in the attention process, that's the one that maps the conditional mean, is effectively a loading matrix. The interpretation of the embedding dimension is this S matrix that allows you to recover the factors from the original data. And then H, the number of heads, is the rank of the lagged coefficient matrix of the dynamics of the factor, and this is going to be restrictive whenever H is lower than the minimum of L or R squared. Summary so far, we have multi-head attention as a parsimonious observation-driven model of time variation in the autoregressive coefficients. And it's also giving us quite a lot of dimensionality reduction. So the interesting bit about this is that, like in factor models, the dimension of the parameters is going to grow very slowly with n, the number of variables. But because of the head reduction, it's also going to grow relatively slowly with the number of lags. So if we want to have systems in which we have a lot of variables and a lot of lags, which we know that might be a good idea, this is potentially a useful model. And as I said, these dimensions are closely related to concepts that are familiar from factor modeling. Okay, so this is the only slide that I'm going to have on the covariance matrix. There is actually, as far as we can tell, little guidance in terms of the machine learning literature. Most of the work there targets point forecasting, but as we know very well, in macroeconomics, predictability in finance as well is really low. So having a good modeling of the covariance is actually pretty important. And there's also a practical consideration that I will mention later. So what we've done is we've tried to come up, and we're open to suggestions here, but we've tried to come up with a way of modeling time variation in the covariance matrix that mimics the way that is modeled in the conditional mean. And in particular, the two important features are that we don't want to have latent objects. Everything is going to depend on past observations, which is going to be critical for estimation. And the second thing is that we want to have this idea of dimension reduction that is kind of matching what we have in the factor model structure and in the conditional mean of the attention. Now, one thing that is important is that there is no particular reason that the dimension, so here we've modeled Q common and N idiosyncratic shocks. In the traditional static factor model, you would have the dimension of the number of common shocks would be equal to the number of also common factors in the conditional mean. But here, it's not necessarily the case. So we just say we could have Q common shocks, but maybe the structure of the conditional mean is actually smaller than the number of aggregate shocks. Okay. How am I doing with time? Okay. So, 20, huh?
Jesus, red card.
I keep thinking it's 40.
So like Thomas, I can relax because I was rushing.
There is a bias in the algorithm that is running to decide the time.
Okay, so yeah, it's okay. We can finish early and we can go have some beers. So let me talk a little bit about estimation. Even though this is a model that provides quite a bit of dimensionality reduction, given the small samples that we typically have, especially in macro, it might still be a very good idea to engage in some shrinkage. And in particular, something that we know, from the work of Sims and his students from the 1980s is that you can develop priors that are well suited for economic time series. And I saw a lecture of Sims that basically said if you could take a random time series from Fred and you don't know what it is, what would be a good characterization of it is probably something like a unit root or a random walk. And that's kind of the basics of the Minnesota prior. So the question is, now that we have this mapping between the attention model and the models that are, familiar to econometricians for the last 40 years, what we can do is we can actually design a prior that puts us back into the old world and allows the data or the posterior to deviate from that prior if we are in need of it and if it's something that the data is calling for it. So in particular, we're going to say we're going to put the prior on the time invariant specification. That's going to be the center of the prior, and we're going to shrink towards that. It's very easy. Remember, I had this, this score that is basically driving the entire time variation of the model, and I said before there is a particular point. If we set these f's all to 0, then we have the time invariant case back. So instead of setting it to 0, we're just going to put a prior that this parameter is effectively 0, but it may deviate from 0. I also mentioned that we're going to have these BL terms that are not present in the original specification, and I said this is going to be important for us in a time series context. So why is it the case that it's important? Because if you now look at this expression and you set all of the f terms to 0, if that BL was not there, those scores will all be 0. You plug those back into the softmax transformation, and what you would get is that a priori, all the lags receive equal weight. And my interpretation of this is that perhaps for language, it is not the case that, if I give you a paragraph, the very last sentence of that paragraph is particularly important. Maybe it's the first, or maybe it's something in the middle. It's kind of uniform over that. But we know, and we think that in time series, the last few lags are probably going to be more important than the lags that are in the distant future. And therefore, we need those terms in order to be able to have a priori more weight on more recent lags than distant lags. Okay, so we're going to have to calibrate that in a way that is effectively mimicking the work that was done 40 years ago by Sims and Litterman and company. And the nice thing about this is that we're actually going to be able to do this in an elegant way, in the same way that they did, using artificial observations that you add to the model and that target certain coefficients. I'm not going to go into the details of this, but they are in the paper. How do we estimate this? Okay, so the key thing is that these head states are deterministic given the past observations and given the parameters. So the posterior evaluation is actually pretty easy. We don't have any need to do Kalman filtering or particle filtering, anything, even though the model is nonlinear. And in fact, the sampler is partially conjugate. So there are some parameters that are effectively closed form draws. For the rest, we're going to use the elliptical slice sampler, which is my co-author's favorite tool. If you're not familiar with it, you can think of as a Metropolis Hastings update that is extremely efficient whenever you have a Gaussian prior. This is just to give you a sense of the computational aspects of this model. Okay, so I have in each of the rows is just number of variables in the model. And we want to try to push this to say, we know that small VARs and VARs with small number of lags from the work of Christian and others maybe are not a good idea, so we would like to have bigger systems. So I'm kind of putting there potentially a large number of variables, and I mean 12 is not that big, but let's say a generous number of lags. And then what I'm saying is like, what is the time to produce 5,000 draws, 5,000 independent draws? So the Bayesian VAR is actually extremely efficient. This is a conjugate sampler, so we can actually generate 5,000 draws in 2 minutes, even if we have 200 variables. Okay, so this is extremely efficient, but of course it's a constant VAR. We could try to do a kind of canonical implementation of a time-varying VAR. This would be the model of Giorgio Primiceri. If we try to do it even with one variable, it's kind of already, I mean, this is kind of nothing. But look, if you go to 4 variables, this is 30 minutes. and I checked, I believe this number is actually 2 weeks. If we wanted to try to do a time-varying VAR with 15 variables, I did not even attempt the larger systems. So as is well known, we can do time-varying VARs. We have been able to do that for many years, but it limits us to 3, 4, 5, maybe 15 variables. Here, this is the column for the attention model, and you see what you gain from the computational efficiency of the system. This is why this model has become so popular in machine learning. So you can actually do these kind of things, even with 200 variables in just a little bit above 1 hour. Okay. So let me finish with some application. And, Juan and I are debating vividly about what is the best and most interesting applications. There are several that we could think of.
So can I just
Yeah.
try to understand what is the point of all this?
Yeah.
So this is a very efficient way of running time-varying VAR?
Yeah. It's a very efficient way of running time-varying VARs.
Both computationally and...
But apart from the efficiency, what I think there is a nicety, which is that the efficiency also have a very natural economic structure and interpretation.
Okay.
Yeah.
I understand that. Okay. But yeah, okay.
Yeah, and it's also basically connecting to this gigantic literature that is completely outside of economics, that is revolutionizing the world and claiming fantastic properties of this class of models. Chris?
Just to elaborate a little bit more on the niceness of the interpretation. So I guess you're making 2 points. I think the economic interpretation, I was following that argument of the relation to factor model interpretation. So we think those are kind of a decent description of historical time series, right?
Right.
There's no, as far as I can see right now, kind of more connection to say what a structural macroeconomic environment would be inducing. And I think that would be very nice to see. Like, I think though, because your second point is more like, yeah, it's great what these tools are doing in another domain, but for us here, the objective is, I guess, in your kind of a reduced form sense, forecasting, right?
Yeah.
And it's not exactly obvious to me that what's appealing there is appealing for forecasting purposes, right?
Yeah. So I totally agree, and in fact, that's where we're going. As of this version of the paper, I don't think we can claim yet that we can use this model to approximate some sort of underlying nonlinear kind of general equilibrium structure, but that's actually where this is going. Okay. It's just that we don't have it yet. But I think this is kind of the natural. In fact, the second application that we have here is already hinting at that, when we can think of this kind of literature on state dependency a la Auerbach or Kornichenko as a very nice application. This is still empirical, but we could also think of trying to approximate a nonlinear or regime switching DSG model without exactly knowing what is the source of this. I will say one thing about this, which is that there is one restriction, which is kind of present even in the multi-head model, which is the fact that the long-run persistence matrix, this B that I have been mentioning, is still time invariant, and that is quite restrictive if you want to do the kind of exercises that you have in mind. But we're working on relaxing that. So today what I'm going to show you is just an exercise that takes this model and takes a canonical macro data set and asks the question, okay, we have this kind of pretty flexible model that expands the VAR in various directions. Now, what is important for macro data? Is it the time variation or is it the rank reduction? And the way that we try to answer this question, I mean, there's other ways of answering, but the way that we've done here is to say, look, let's take the data, estimate the model until the end of the Great Recession, and then do an out-of-sample forecasting exercise with many different specifications in which we're effectively either tightening the prior, shutting down the time variation, or tightening the dimensions of the system, making it more and more restrictive, and then see which one outperforms the constant VAR as a way of answering the question, like, what is the data calling for? And, are any of these rank restrictions or the time variation actually helping us if our objective was to forecast? So here are 2 charts. In the left hand, what you have are models. So here, various models are pulled here. The y-axis are basically these attention heads. So how much am I restricting the lag coefficient matrices of the factors? On the x-axis are the number, the embedding dimension, in other words, the number of factors. And then on the 2 charts, one is where I have the time-varying covariance, and here is the constant covariance, okay? Whenever you see blue, we are doing worse than the time invariant VAR, and whenever you see green, we are doing better. So first key message is that models in which we are allowing the mean to move around, but the variance is not moving around, generally underperform a constant VAR for this data set. I think this is not surprising, but what is effectively happening is that we are allowing the mean to vary, and in the data there is quite a lot of heteroscedasticity. So the conditional mean seems to try to be adapting and moving around in order to fit the conditional volatility. And this is actually a point that was done already many decades ago in a discussion between Sims and Cogley and Sargent. So we find exactly the same result here. Once you go into models in which we allow the correlation or the covariance matrix to move around, what you see is that actually the specifications that do well are those that have a factor dimension that is smaller than the number of variables. Here we have 7 variables, and you see on the horizontal axis, the more you go to the left, you generally do better. The numbers inside of the boxes are the ratio of the root mean square error for GDP relative to the VAR. So 0.68 in the bottom corner effectively means that we are doing approximately 30% better than the VAR, this is a large difference. And this is specific for the GDP, but if I do this for any of the other 6 variables in the model, you get results in the same order of magnitude. So this is pretty meaningful. And it's interesting that we require a small number of factors, but a relatively generous number of heads. The number of lags here is 12, both for the B-bar and for the attention model. So it's still less than 12, but it's relatively generous. And now let's look at the priors. So what if we set different tightness of the prior that controls the time variation in the conditional mean? So in all of these models, the conditional correlation and the conditional covariance is moving around. But then as you go to the left, we are having a tighter and tighter prior against time variation in the conditional mean. And what is interesting is that actually the models where the prior is very tight and we're stopping this F matrix from deviating from 0 tend to do better, at least for this data set. So the preliminary conclusion that we have here is that if we're interested in modeling this particular group of variables for this particular sample, it looks like the first thing that you should add is time varying volatility, and conditional on that, it looks like tighter priors on the time variation of the conditional mean are better. Okay.
So Sims was right.
Sorry? Sims was right, yeah.
Something I learned in my life, Sims was always right.
It seems like a true statement.
Yes.
Yeah, it's a true and eternal statement. Okay, let me conclude, I think, 5 minutes ahead of time. So, we have now mapped this model into the language that many of us are familiar with, and it turns out that we can understand the attention model that has revolutionized the world as a time-variant VAR with rank-reducing restrictions. These restrictions are closely connected to those in factor models and have a natural economic interpretation. And as Chris was saying, I think the next step for this line of research is to try to say whether we can approximate arbitrary nonlinear general equilibrium data generating processes. Interesting thing is that Bayesian inference for the samples that we typically have is feasible and is very efficient. No filtering is required, and we can develop priors in the spirit of Chris Sims. And we think that this class of model is a promising avenue to flexibly model time variation and state dependence in macroeconomics. Thank you very much.
Very good. The good news is that Luigi will be running it tomorrow.